converting up to cold flash.
Oh, very cool.
What's the stable?
It should be just on that kitchen bench.
Oh, yeah, it does really. Oh, yes. You know what this point is? We have a
Some because you have to like the only way to get a goal is to like be the best in the company. That's kind of weird. Yeah, there was a year where you got 28. They got equal 28. So Gunny got 28, and you got a silver. See, I reckon like people might not necessarily because there's some people I see them get like 12, right? You see the question they do with like, yeah. It's like really the easier way to get 12 points. Yeah. Or like they get 12 and it's like 6 from question 4, 6 from question 5, and like 2 from question 3. It's like what? Well, you know, like 5, 5, 2, yeah. I'm like, it's probably the hardest way to get 12 in the world. Yeah. Like if this is not at least an honorable mention, there will be no honorable mention. Yeah. Yeah. Yeah, it's very bad. Nobody got 76 for the first 2 minutes. Yeah. That's why we go for like 2 questions. It's just like, it makes some strategies more viable for question 3 if you're like spending a lot of time. Yeah. Because like you can compare like you want to go to the US, people in the US do this. Yeah. Like just even making it seem like yeah. Like I reckon anything that you can sort of compete with people in the US is really yeah. Yeah. meet you in here. Oh.
It's all here somewhere, huh? It's all here somewhere. Scheiße. This is why I didn't try to do too many problems. And then, like, not immediately before the day it's due. Because then, like, now I don't know where all the problems are. Alright. Shall we go through that one we just did? Question one.
Yeah.
Oh, let me just go through some stats.
Cool. Okay. Let me write that something.
Yeah, so I guess what we've been focused on is like doing the APMO question 1 and 2, yeah?
Yeah.
I think that's a good thing to focus on like year 11. So get the question 1 and 2. I feel like if you're doing really like if you're on a roll, you could probably get it both in an hour. Yeah, that's like one
I
extreme.
got like wait, I got the first one.
Yeah. So like, I think that's possible, but I mean, obviously we just did 2017, and that's unlikely for that. Yeah.
Yeah.
But I think for like 14, 15, 16, I can't remember 16. Definitely possible for those other 2 years. Yeah. And then you're looking at question 3. Okay, so I mean, to be like not so ambitious, if you just get question 3 and 1 and 2, okay, like with the rest of the time, that's like 21 points. It's
Yeah,
like
that's pretty
way.
good.
It's like if you're looking at the stats, like most years, like if you get like 12 is like top 10 kind of thing. You know, like there were some crazy years where 2 people got 28, right? But then it was like 23, 22, and then like if you got over 20, you're still in like the top 4 or 5.
Yeah.
Okay. So 3 questions is pretty crazy, and usually like you see people skipping a question, 4 or 5, and like getting 28 is like a really good score. Okay. Like there was like the one we did last year, no one got over 28. like all of the people. So, and those people went on to get perfect scores in IMO and stuff like that. So it's like it's a time thing, right? You only have 4 hours. I think if you can get this in like 1 hour, you're doing pretty well, and maybe you can like choose in 2 hours, right? I mean, how realistic is this? Well, I guess we can have a look at the questions, right? Yeah, I feel like you guys are at the level where like you should be able to get question 1 and 2. Like, I think you should like question 1. I feel like you should be able to just get them. I don't know. This year was a hard year for some reason.
I suppose it's just one observation about parity.
Yeah, the parity is pretty good.
Yeah. And I do feel like the question 3, 4, and 5 they do jump in difficulty.
Yeah.
Like I've seen it. Like I don't think you can necessarily feel the jump in difficulty from 1 and 2 because maybe you're just stronger at one of the areas that they ask. You know, like. So there's definitely situations where I've seen question 2 feels way easier than question 1, especially if like if you like algebra and question 1 is a geometry question or something, or the other way like is normal. But when you get to question 3, I always feel like there's a bit more of a jump. Like there's always some distance. Even if you're feeling good about the question, there's a bigger distance from the feeling to the solution, And I think 4 and 5, I'm not sure if it's like another jump because we haven't really tried that much this time. But they definitely don't have to be in order, Because we've seen lots of times where people skip 4 and do 5. Okay. So we're just focused on 1, 2, and 3. Okay. And then maybe we can do 4 and 5 next year. We only do 4 and 5 next year. Next year's exam. Okay. Yeah, so let's do question 1. Okay, what was question 1? It was like, it was kind of a weird condition to start with, yeah? So I felt kind of like it was a hard question because like there weren't very many simple ideas. You know what I mean? So we had like it was like question 1, 2017. Like 5 tuples. And they had to do this.
It's like a minus 50.
Right? Yeah. And then you put 2017 of them in a ring, yeah? And like what are all such combinations, yeah? And the thing is like the 29 is a pretty strange number. Okay. 2017 is a pretty big number. And I don't know, when I looked at this I felt like there wasn't like very many easy ideas. And there was lots of ways to go wrong just with even interpreting the question.
Yeah.
Like for example, you could reorder the 5 things to get it to do that, So like if you do the like 5 and then the next 5, it might not be like in the same order, right? But I guess you notice that like reordering it just changes the sign. It doesn't necessarily it doesn't do anything much more complicated than changing the sign. Okay. So what do I have here? Yeah, so after staring at it for a while, the first observation. Oh yeah, the first observation was you could change the 29 to a 0. Okay. So one way of seeing this is, because I guess I was trying to say, like, for example, I was trying to split up the 29 between the 5 numbers, right? So like if you put 5 with A, 5 with B, 5 with C, 5 with D, and 5 with E, right? Then it sort of should like equal to 4. You know what I mean?
Yeah.
But the problem is a plus or minus, right?
Yeah.
So if you put A is +5 and B is +5, well, that'll make it -5, right? But then you notice that there's 3 plus signs and 2 minus signs. So you can actually plus whatever you want, right? You can actually add 29 to all of them.
Yeah.
Or subtract 29. One of those, and there will be a 29 out left over that'll cancel the 29. So you can kind of think of this as just A plus B plus D equals 0, yeah? Okay. And I guess thinking of it like that made it more obvious that all zeros is a solution. Yeah?
Yeah.
You don't have to worry about how things match up. Like if they're all 0, they're going to be 0 everywhere, right? So then you get all zeros, right? So all zeros is a solution, and then so if you convert it back to what you had originally, then that would mean all 29s is a solution, right? So if you just had 29, 29, 29, 29, yeah? Okay. That would be like a solution. Okay, then the next thing, well, actually, this kind of was in the back of my head for a while. It's kind of like you have a lot of linear equations, right? They're all linear equations. So, how many do you have? Well, you have 2017 of them. All right, so you have one for every variable, basically. Okay. So, if all those linear equations were somehow like independent of each other, right? Then that would force there to be a unique solution. Okay. So I expressed that in the only way I knew how, I guess, but you can kind of translate it into easier terms. So I drew a matrix, okay? Is this red better? So what I kind of want is that I want so if we consider that the first equation, right? The first 5 variables, I want to be on like here. So the first equation I represent with the first row is like 1, 1, 1, 1, 1. So these could be plus or minus ones. So because we don't know what order it is, yeah. So like any of them could be plus or minus 1. Yeah. And then we put zeros for the other variables. Yeah. Does that make sense? So basically, we're just writing the coefficients of the equation. Yeah. So can you see the next one will be like 0, plus or minus 1, minus 1, all the way up to here, right?
Yeah.
And then zeros. Yeah. Okay. And so can you kind of see it's going to go like down the diagonal until you kind of get to the end?
And then it starts at the beginning.
Yeah, so when you run out, and there's only 4 entries, right?
Go back.
When there's only 4, then the last one's on the first, yeah? And there's all zeros, yeah? And then like this. There's 4. There's only 4 at the very last one, right? And there's 1 at the end. Yeah?
Yeah.
Okay, let's line these up. Yeah?
Yeah.
Alright, so what does it mean to be independent for equations, yeah? So for example, can you see if you get a matrix that looks like this? If it's like 1, and it's like zeros here and some other stuff here, yeah? Yeah. Like if the matrix looks like that, right?
Yeah, then it's
Then that's, you can solve it.
Yeah.
Yeah? Because basically, how would you say this? So
each one corresponds to the social of each.
yeah, so like you can so what the first one tells you, right? Since it's the only one,
Okay.
um, let me explain this. Yeah. So can you kind of see like you can add and subtract equations, right?
Yeah.
So like let's actually not have an x here. Let's pretend this is all 0, yeah. Can you see that that's just saying
That's the answer.
x equals 29? Yeah.
Yeah.
That makes sense.
Yeah.
So if it was all zeros, you're good, right?
Yeah.
But like if they're not
But you
zeros,
can make
you're
them
not too
zeros.
far off from being zeros because you can subtract the second equation from the first one to clear that to get a 0.
Yeah.
Yeah. And then you can use that one to make that a 0. Use that one to make that a 0. Yeah.
Oh yeah.
Yeah. So basically, you're allowed to sort of add rows to each other. That corresponds to adding equations to each other, right?
Yeah.
And that will preserve whether the system has the kind of solutions or not.
Yeah.
And in this case, we only care about if it degenerates, right?
Yeah.
So all we need to know is that adding rows to each other makes it more degenerate, right? Or equally degenerate.
Yeah.
We don't need to just say it equals degenerate. As long as it's equal or more, and at the end it's not degenerate, then it's fine at the beginning too, right? Okay. So can you see how it starts off pretty well, yeah?
Yeah.
So if without this crap here, then
You'll be.
it'd be fine, yeah? You could
Yeah.
be like that and you can just solve it.
Yeah.
So it's really just about getting rid of this stuff.
Yeah, but you don't know if it's possible.
Yeah, you don't know if it's plus minus, okay? But this is where the parity comes in, yeah?
Oh.
So you don't know if it's plus or minus, but you do know it's odd, yeah?
Yeah.
Okay, so for example, okay, let's look at the first row, right? So let's try to clear the zeros, make all the other entries 0, right? So we can subtract this from that, yeah? To cancel that 0, yeah? So you can make this a 0, yeah? That makes sense?
Yeah.
Like no matter what it is, you can just match them up, yeah?
Yeah, you can.
Okay. And then this one, we don't know if that's going to be 0 or not, right? But we know it's going to be even.
Oh.
That makes
Yeah,
sense?
yeah. So all the other ones are equal. Wait. Apart from the last.
Yeah?
Yeah.
So we've designed it by subtracting the second row from the first row
Oh,
to clear that 0, right?
Yeah.
And the others, we don't know if they're going to cancel or not. But we know they're going to be even.
Yeah.
Right? Okay. So then when you're doing the next one, okay, you see when you clear the third row, you use the third row to subtract from the first one to try to get that into a 0, yeah? To make this a 0, yeah?
Yeah.
You have to subtract it twice, yeah? Because it's even. Or you have to subtract an even number of times, yeah?
Yeah.
So then the other stuff stays even. Yeah.
Oh, okay.
That makes sense?
Yeah.
It stays even. So you keep going, yeah?
Yeah.
Yeah. So basically, they're all zeros, right? So you keep making the front part 0.
Yeah.
And you're creating a bit of a mess at the back.
Yeah.
But it's all even.
Yeah, and I guess you can fix it off.
So the mess at the back is all even. That makes sense? Okay. So then, but as you're fixing it afterwards, right? Yeah.
Yeah.
So you can go all the way down to the bottom corner and make them all 0, right?
Yeah.
But then there's one extra problem, is that these other rows in the bottom is
Yeah.
creating more of a mess at the beginning.
Yeah.
Okay. But that's okay because we know that it's even. See? So once you get to here, right? Once you get to this row, yeah, you're trying to make this a 0, yeah?
Yeah.
Okay? But the problem is this has an entry here, right?
Yeah.
That might interact with this.
Yeah.
Yeah?
Yeah.
But we know this is even, right?
Yeah.
Okay? So when we subtract off that, we do it an even number of times. Yeah?
Yeah.
And this is a 1 or a negative 1, so it's odd, right?
And then
Yeah. So it can't cancel it.
Okay.
So stuff happens here, but it keeps it non-zero.
Yeah.
Yeah, because it's odd.
Okay.
Yeah.
So you could cancel out that one.
Yeah. So basically, what happens? Yeah, and it happens for every other row too, right?
Yeah.
Once you go all the way down, like all this stuff is messing up here, making them all 0, and it's messing this up in an even way, so it stays non-zero.
Okay.
Yeah.
Yeah.
So then the result is you get a whole row of zeros and a number here that's odd. Yeah.
And then you just divide.
And then you just
But you mess with times to the 4 as well.
Wait, don't you just cancel out the bottom like plus minus one so that they become 0? And you know it'll be like a even number of times, so you won't change it.
yeah, like I guess this way I get to do it all in one go. But yeah, basically you can do it in a lot of ways. But can you see like? So if I'm just clearing, so I'm doing the same thing. I don't want to change it up too much, right? What I'm doing is I'm making these all 0, yeah?
Yeah.
And I'm making sure that the first term is non-zero. Does that make sense?
Yeah.
And that happens, right?
Why?
Because the only time that this term gets messed up is when you get to here, right?
Yeah.
But we're subtracting an even number of times.
Yeah.
So 1 plus or minus 1 plus an even number or minus an even number is going to stay odd, right?
Yeah.
So it's going to stay non-zero.
Yeah, but how about like the second to the third and the fourth term?
Oh, but it's also still even.
Yeah, they're
so-
still doing it even number of times, yeah?
Can't that also be non-zero?
What?
Like after you do the subtractions, your first 4 numbers are messed up.
The first 4 numbers.
Yeah, because once you get to the bottom one, you've unmessed up you've turned all the other ones into zeros. But in the process of doing that, you've messed up the first 4.
Oh, maybe I don't need to do one. Okay, so hold on. So I've cleared out this 0, yeah?
Yeah, that one is definitely the first one is definitely non-zero, but the other 3, the next 3 could also be non-zero.
Yes, 3. Oh, I see what you're saying. Yeah. So maybe this is not very efficient, but it still works, I guess, doesn't it? So oh. Okay, so we're at the point where this is a 0, right?
The second one.
So at this point, everything except for the first one. Everything except for the first one and the last 3. And last 4.
Hmm.
Do you somehow prove that like something is always decreasing?
This should be enough to show it. I mean, I just haven't been careful with this particular way of saying it. Okay, so yeah, so okay, so as we're clearing out all the zeros, yeah, we get this entry is being messed up, right?
Yeah.
This one's being messed up a little bit.
Yeah.
So the first 4 entries are getting messed up a little bit. Yeah.
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 The first one should be fine.
Okay, but the parities are still the same, right?
Yeah.
Okay, so once we've messed them all up, we get these 4 are non-zero and all these others are 0. Yeah.
Yeah.
And then you could still use this to clear out this column, yeah? Hmm.
Yeah, and the sort of vector things. The things as well.
So maybe it isn't as nice to try to clear out those zeros first. So the thing I originally had was
But if you just like try to get rid of the plus minus one, the other if you're done.
here.
Yeah, if you clear out plus minus, then you get like where all the stuff on the diagonals to instead of like clearing it all.
Yeah. So I have evens there. Clear those. Yeah. I guess even though you can't see it explicitly, can you feel the progress of clearing that first column? Like if you can clear that first column, right?
Clear the first.
So-
Doesn't mean we keep the first one.
Huh?
Doesn't mean we keep the first one.
So we want these to be all zeros.
Yeah, you want everything at the bottom left one.
So we want all these to be zeros,
Yeah.
and then we're
Oh,
good.
yeah.
Yeah.
Yeah, so why are you clearing the like ones and like these zeros?
Oh, so I cleared these ones to be zeros so that I can use the first row to kill off the
okay.
other stuff. Maybe it's cleaner if I do this one at a time. Like, what if so instead of clearing all the zeros here, right?
Yeah.
I just cleared it up to here,
Okay.
right?
Yeah.
And then used it from here to kill this one. Yeah. So instead of clearing it all the way to the end, right?
Yeah.
I clear it up to the red 0 here. or maybe just the one before. Yeah. And then I can use that row to kill this one here.
Yeah.
Yeah. And then this is still non-zero. Yeah. Because the even stuff here.
Yeah.
So there's some stuff here that might not be they might not be zero, but they're even.
Yeah.
So you killed the first one without killing
Yeah.
the last one. Yeah. So how'd you get rid of like the second one?
Yeah.
The second, the last one.
Good question. So
Maybe just do the same thing, but like here use the second row.
yeah.
Bring the second row down. But that still leaves stuff for like
Maybe you can
the very last.
you can use like the second row to eliminate them.
Yeah, so I guess maybe instead of going there, then here, maybe we can go there and there.
Where can you use the second row to eliminate the second column? Do what you did on the first one.
Yeah. Yeah. Yeah, I guess I'm sure this works. It's just got to be a bit more careful about saying it. I thought it'd be more trivial than that. But at least you see what we're trying to do, right?
Yeah, you cancel it.
Cancel these zeros with these row additions.
Yeah.
Okay. Yeah.
So what happens like say if we do that, what do we do?
Okay, so once it's zeros, right?
Yeah.
Then it's like that, right?
So we can get an individual expression for each time.
Yeah. So like A equals something, B equals something, C equals something.
Yeah, but if you just
So there's only one
you
solution.
don't need you don't need the rest like the top right side to be all zeros.
Yeah, no, you can
It
can
can be
conclude
anything.
it from just the
Yeah, just like the bottom
ones. You
So-
can conclude it with just non-zero on the diagonal, zeros below the diagonal.
Yeah, so like if you use the second row, if you do what you did like on the first row, the even thing, if you use like the third row and the second row,
Yeah.
you eliminate the rest to zeros, then you prove that like that one's still non-zero. You can use it to kill the second column as well. Right? If you do
Yeah.
that for third and fourth, then
Yeah, I mean that's what I had in my mind, but I don't know why I can't say it very explicitly. But yeah, that's basically what I'm trying to do. So yeah. So basically you're just subtracting like this first row from these to clear it out, right?
Yeah.
And you're kind of keeping track of the interactions with the non-zero entries. And the idea is because of the parity, they'll end up doing what you want. Yeah. But for some reason, yeah, could be more explicit than that.
yeah, but that does work.
Yeah.
Yeah, it works. Just,
Yeah, I was sure it worked before, and then I didn't even write it down, and then I forgot. So I guess.
because it won't affect like the second, third, or fourth column. It's all zeros if you look like the first row subtracting. And it won't kill like the fourth last one because the parity, right?
Yeah.
And like the same thing should work for the second row on the left.
Hmm. Yeah. So maybe it might get a bit dirtier before it gets cleaner. Yeah. There might be some weird stuff happening here, but like as long as you're kind of getting more zeros all the way across, it's gonna clean up to something like that. Yeah.
Okay.
Yeah. What's next? No, I was thinking. Yeah. Okay. All right. Which year do you want to go for?
I'm gonna go through question 3 please paper.
Oh.
Try that.
We'll have to save the brainstorming.
Yeah.
For a little while. So
How about 2014 question 3?
Yeah, 3.
That would be very
Did you answer?
Hmm?
Did you answer?
yeah, I already did, I did all of these, but yeah, we'll see how it goes. All right, race. All right. Where is it? So this is 2014, question 3, yeah? And the question asks, at which end does there, is it for all k or is it the six?
Yeah, 4, okay, there exists.
For which end such that for all k there is this a a cubed plus a minus k equals 0. Is that right? It's divisible by n, yeah? Yeah. You try this one? Okay, so what did I do? Alright, so n equals 1 works. But I guess that doesn't really mean much.
I'm pretty sure n equals 2 does
N equals 2 doesn't work.
because you get like something. If it's negative 1.
Yeah. So at what point n equals 4 doesn't work? So 2 no, 3 yes, 4 no, right?
I'm pretty sure 5 doesn't have.
Yeah.
Oh, you did 63.
Yeah. So I think at this point I made some observations. It was like yeah, so while doing n equals 4, yeah, I realized what you have to do is so like a cubed plus a has to get you all the values mod n. Yeah. So basically you need like this function z mod n to z mod n, right? To be onto. Yeah? Or another way of saying that is you want it to be injected. Alright? Because injective is the same when it's finite. Yeah? Alright. Did any of you think about quadratic reciprocity at all?
Yeah, you probably use it to find like the like whether there's
Yeah.
like inverses or something. So to prove that it exists, like the that thing more than actually exists.
Yeah. So for example, it's injective, right? Like 0 goes to 0.
Yeah.
Nothing else can go to 0. So if a cubed plus a equals 0, right? That's a problem.
Yeah.
Yeah. So a is a squared plus 1, right? So if minus 1 is a square,
Yeah.
mod n, right? Then that's all. That those ends are not going to work.
Yeah.
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 So I think that in and actually you can kind of see like any prime for any prime, right? For which minus 1 is a square, yeah, mod p.
Yeah.
It's not going to work. Like if that prime divides n.
Right.
Because what's happening? Okay, so one other observation, I guess. I don't know if I made it clear. The thing is, like, this is a function from a set to itself, right?
Yeah.
It's injective, yeah?
Yeah.
It's like a bijection.
Yeah.
But not only does it have to be a bijection, but all iterations have to be a bijection, right? Like, if it's injective once, it has to be injective forever.
Yeah.
Does that make sense?
Injective for,
Yeah, like,
let's say,
huh?
something.
Like, if you compose the function with itself over and over again,
Yeah.
it has to stay injective, right?
Right.
So like,
Oh, yeah.
yeah, so like, going to 0, like, if something goes to 0 that's not 0, that's directly bad, right?
Yeah.
But because it iterates, right, even if it progresses towards 0, it's bad. So, like, ways of progressing towards 0 is like, because you know how, like, mod n, not everything's nice, it's 0 divisors, right? Like if n is 6, 2 and 3 are both bad, like, in terms of, they're not 0, but they're getting closer to 0. You know what I'm saying?
The number can make it.
So, like mod 6, right? 2 and 3 are 0 divisors.
Yeah.
So they're not 0, but they kind of like, they got some, they've got like some part of them that you can't get back. Like they're not invertible, right?
Yeah.
Yeah. So like if you have a prime that's you know, minus 1 is a square in that mod p, right? That means p divides this a squared plus 1, right? Yeah. So you're adding a factor of p when you go through the map, yeah? And if p divides n, right? Adding a factor of p makes it a step closer to 0.
Yeah.
Does that make sense?
For like all points.
Yeah, I think so. So for any prime, we'll see the factors a is here, right?
Yeah.
A's already got its factors here. So if you can get another prime here, so I mean, it's actually explicit which primes have squares equal -1, right? Because it's like a formula. So you have -1 to the power of p minus 1. Yeah. So that's equal to 1 basically. Wait, is it 1 or -1? It's 1, right?
Yeah.
So that's true for p equals 1 mod 4, yeah? So, I mean, if you just let n equal p, right, then it's clear that this is going to 0. Yeah? Like if p is 1 mod 4, yeah?
Yeah.
Then there is an a for which -1 is a squared, yeah?
Yeah.
That's what this is saying. Like this formula is telling you if this is equal to 1, then this -1 is a square mod p. This is like, this is equal to -1. The Legendre symbol thing. So basically we have this thing that says if -1 to the power of p minus 1 on 2 is equal to 1, right? Then it's a square mod p.
Oh.
Yeah?
Okay.
And if it's equal to -1, then it's not a square mod P. And it can only be plus or minus 1. Alright. So, yeah, I mean, maybe instead of thinking about the condition, maybe you can just think if it's -1's a square mod P or not. Yeah. Okay. Because you won't actually need to use it. You just need to know there is such a thing. If anything's a square mod P, then -1 plus that will be 0, right? Yeah. So for that P, right, it's gonna be not 0, but it's gonna go to 0 mod P. Yeah. So it's not gonna be injected. So basically, this condition fails for all the P for which something squares to -1. Yeah? And clearly 0 can't square to -1. Right? So something else has to square to -1. And whatever that something else is, you let that be A, and you get 0. Yeah? Does that make sense? Yeah, so if A squared equals -1, then A squared plus 1 equals 0. That's all we're saying. Mod P. Okay, so I guess, yeah, so for P, it's explicitly failing this condition, right? And I'm also saying for anything that P divides, it would also fail the condition. Yeah, it's a bit more heuristic, but basically because you're now getting a factor, you're making it like, you know. So for example, if it was like a power of P, okay, right? And you're adding a factor of P every time, eventually it'll be 0, right? Does that make sense? Okay. So that's a pretty key observation, yeah? Stuff like, did you make the observation that powers of 3 work? Yeah, could you prove that?
Yeah.
Okay, so let's prove that. Let's prove that.
Essentially, just prove that all AP plus A are using because it's saying
Yeah. So like maybe a more formal. So you have A cubed plus A, right?
Yeah.
Equals B cubed plus B. That's like if it's not unique, right?
Yeah.
And then you can factorize it. Like A minus B outside of A squared. Yeah. Plus B squared. Plus 1, right? Yeah. So mod 3, right?
Isn't it?
Yeah, so mod 3, okay. For these two things to be equal, mod 3, yeah? So actually we know that they have to be equal, A and B have to be equal mod 3, right? Yeah? But that's what working for 3 means, yeah?
Yeah.
Okay, so now we can assume it's a power of 3, yeah?
I divided by A minus B.
Divided by A minus B.
So that I think that seems like maybe
I think what I showed was, so basically like if you have mod 3 to the n, right?
Yeah.
3 to the, whatever that is not taken. 3 to the L, yeah? So I wanted to show that, yeah, so this is the equation you get, yeah? Okay, so I wanted to show that you can divide by this, yeah? And then you get A equals B. That would show it's injected, yeah? Okay. How can you show you can divide by this, right? Yeah, so it can't, so it has to be co-prime to 3, yeah? Because if any time it has a 3, it becomes a 0, like it's not invertible. Yeah? So you just have to show like mod 3 is not 0, yeah?
Yeah.
But we know that A equals B mod 3, right?
Yeah,
We do, don't we?
that's clear that it's
Yeah. We know that they equal mod 3 because that's one of that's like the base case. Yeah. And if they equal mod 3, that's going to be 1, 1, 1 or 0, 0, 0, right?
yeah.
So then this part is going to be 1 mod 3, yeah? It's invertible. Mod 3 to the end, yeah? So then you can divide that, yeah? And you get A equals B.
Yeah.
That makes sense? So that proves it works for 3 to the end. 3 to the L. Yeah?
Yeah.
Okay. Let's keep going. Oh, I think I made this observation that the evens were not going to work at some point. Because A3 plus A is going to be even no matter what. Right? And it's got this problem with if it's
If it's always even,
yeah.
you can only get even residues, but you can't get all residues.
Yeah, and even residues is a thing when it's mod even numbers. Because if it's mod and odd, like it's not defined. Yeah. Mod and even, it makes sense to talk about even and odd. And you want all of them to go to everything, but if they all go to even, so there must be some degeneracy, right? Should I have to spell that out? I guess I sort of said that.
Yeah.
Yeah? Okay, so even doesn't work. Yeah, okay, and then this is with discovering powers of 3 works. Sorts of cases. Okay, so that's proving powers of 3 works. And then we have evens don't work, and basically like everything else. Prime is 1 mod 4. Anything that divides is divisible by prime, 1 mod 4. The 1 mod 4 are the ones where the square is -1, yeah? 5, 7, 11, 19, 23, 31 all don't work. Yeah? You try those.
Oh, just okay, not just like original form.
Oh, yeah.
So I need to prove that 4 times of like congruent with 3.
Yeah, so we can prove that, yeah. So let's have a look. Yeah, so it suffices to work for primes. I think I made some observation like that. I guess if you have two things, it's kind of like the Chinese remainder theorem. If you have like two co-prime numbers times each other, right? And like it's like PQ prime, right?
Yeah.
And P has something that doesn't work. You can kind of construct it for PQ. Like you get two things that are equal mod Q. So I was pretty confident you had to just do it for primes. Okay. Yeah, at some point, maybe it was when I got to 31. Because at some point I was like, I went over the edge of being convinced that there wasn't going to be anything that worked. Let me figure out when that was. So I got up to 31. Yeah, okay, so then I started hanging around this condition again, right? Because that was like the proof of the 3 powers of 3, yeah? And it's not really like a special proof, it's like, this is like the only condition you have, yeah? So that's like a key player in this, yeah? Okay, so I'll go back to here, and let's erase some stuff. Yeah. Okay. So look at this condition. So if we want the conclusion to be A equals B, right? Yeah. And if you do it mod P, and if A is not equal to B, you can divide by A minus B. Yeah. So I was kind of looking at what happens with A squared plus AB plus B squared plus 1. Yeah.
It's not true.
Yeah.
Yeah.
I had one idea that didn't work. So I let A equal B squared. And I guess the reason, because I remember there was another question we did with a mystery substitution.
Oh.
Remember that?
That's,
Anyway, so I let A equals B squared, right? What do you get? The whole point of doing that is now you have B to the 4 plus B cubed plus B squared plus 1, right? Yeah. And then that's basically B to the 5 minus 1, but B is not 1. Yeah. Yeah, like you times B minus 1 by both sides.
Oh, yeah, that need is good.
Huh?
That need is really good. Just
Yeah.
like that, just like that, just like that, just
Yeah.
like that. Oh, yeah, yeah, yeah.
What would it be? Well, this. Oh, maybe that's why I didn't work. Oh,
I was completely factors of things we can use like maybe
Yeah.
addition thing.
okay. So yeah, that didn't work for more reasons than just what I thought. Okay. Tried subbing in like A equals 1 on B, it didn't work. Oh. So then I completed some squares. That made it, for some reason, made me feel happy. So if I complete the square, B plus A on 2 squared. Do I get minus 1 minus 3A squared on 4? Yeah?
Yeah.
Oh yeah, so by the way, I guess we've made an observation where we're solving an equation mod P for 2 variables, yeah? Like this is mod P. We're solving for A and B, yeah? Like if we can find A and B, if they exist, yeah? If they exist, it proves it doesn't work, right? Because if it exists, then this is 0, right? So that's a non-injective, yeah? So if A and B,
So you want that to be
yeah,
yeah,
Yeah.
that just may end up with it once. Yeah, that is it. It's like it's no good for zero.
yeah. So we want A not equal to B here.
Yeah.
That makes this equal, yeah? To make it not work. Yeah? Okay. Writing it like this. Maybe I could have been a little bit careful, but see, I like this because we have a 3 and a 4, yeah? Like, we dealt with the cases where it's, we know that 3 doesn't, we know 3 works, right? And we know that 4 doesn't work. Like, we know all the even numbers don't work. So you can kind of move A so that this is just 1. That makes sense? So you can kind of, because A is running through all the values of mod P, right? Yeah. So if you times that by 4 on 3, it's still going to run through all the values. You know what I mean? So it's kind of like this b plus a prime onto
Yeah, it has to.
squared equals minus 1 minus a squared, like that, a prime.
It's the 3 on 4 plus the 3 on
3 on 4 is invertible, right?
Yeah.
Mod p. So if you times it by an invertible, it's a bijection, right? You know what I'm saying?
Yeah.
So if you have the numbers from 1 to p, right? You times it by an invertible number, right? You're going to get the numbers from 1 to p in another order. Yeah?
And then you come back to 3 on 4, so you get it.
Yeah. So since a is just sort of like a dummy variable through all the p, 1 to p, you're going to divide it by 3 on 4. It still runs from 1 to p.
We can just put 3 on 4.
Yeah, yeah. That's kind of what we're all trying to say, yeah? This one too, yeah. Yeah. But then I want to absorb this one into the b. Yeah. So I want it to look like this. So, I have like b squared equals minus b squared plus 1. Something like this. So I think I got this idea once I just let a equal like a equals 1, a equals 2. So we have a equals 2 from here, right? B squared is 2b equals 4 plus 1. Oh yeah. Equals minus 4. B plus 1 squared. Yeah. So basically, I'm thinking of it as something squared equal to minus 4. Yeah. Because this is all going back to this quadratic reciprocity thing. Yeah. So basically, what I'm trying to say is solving this equation, right? Mod p is saying that this is a square. Yeah. Like this thing is a square mod p. Yeah. For some, yeah. That's well, it can't be for all a. Because that'd be like saying it, like the function is like the constant function. But yeah, like we only need it for some a to fail, right? Okay. Does that make sense? So I'm saying here, we need to show that a squared plus 1. So because we know minus 1, we kind of assume minus 1 is not a square already, right? Because when it is a square, we're done, yeah? So we assume it's not a square, yeah? And we know that the product of two things which are not squares is a square. Yeah? You know that? So if something's a square mod p and something's not a square mod p, right? Yeah. And you multiply them together, then they're not. So it's like minus 1 times 1. Yeah? Like the way it works is like this. Like if you have something's a square mod p, yeah? like a to the power of p minus 1 on 2 is equal to 1, right? Or in particular, this is equal to whether or not it's a square mod p, yeah? It's equal to plus or minus 1, whether it is or not, yeah? And if b is the same, right? Yeah. Then the point is when you times them together, okay, you just get a b to the power of p minus 1 on 2, right?
Oh, and if they both not square, then it becomes
Yeah. Yeah. See, because if this is not a square, right, it's minus 1, yeah?
Yeah.
If this is not a square, it's minus 1, yeah?
yeah.
But when you time them together, then it's 1, yeah? Yeah? Okay, so since we know minus 1 is not a square, yeah? Because we're assuming p for which is not a square. When it's a square, we already know it breaks down. Because it already sends 0, something non-zero, 0, yeah? So if it's not a square, okay, then we just need to show a squared is not a square, yeah? A squared plus 1 is not a square. Because then when you time them together, it is a square, yeah? So we just need to show that there is some a for which a squared plus 1 is not a square mod p, yeah? But p is not 2 or 3 or 1 mod 4, right? So it's 3 mod 4, okay? So I guess if you think about the squares mod p, right? So half of the number, half of the numbers are squares and half of them are not squares. Yeah? You know that, right? It's 2 to 1 when you square. Plus or minus go to the 1 thing, yeah? Yeah. So, yeah, so if you think about the function, now instead of thinking about a cubed plus a, think about a squared plus 1, right? Yeah? So, actually, you just think about plus 1. Because a squared is already a square, yeah? So a squared is already a square. And the point is plus 1, okay? See, you need plus 1 to be not a square for some a, right? For something. So you start with the squares, mod p, yeah? You take the function plus 1, yeah? You need that to output a non-square. Does that make sense? Okay. But that's going to happen, okay? Because if they always output squares, yeah? If that function always outputs squares, then plus 1 will always go from squares to squares to squares, right? Yeah? Well, that's a problem because plus 1 gets to everything, right? Like you can output anything you want with plus 1. So, and also, like, it's going to have to work with iterations, right? See what I'm saying? So, like, if plus 1 always takes squares to squares, right? Then plus n also takes squares to squares. Because you've just done it n times.
Okay,
Yeah? But plus n can always get a non-square, right? You just find a non-square and look at the distance from the square and then plus that distance, right? So you can always have a square that's a non-square after you plus 1. Yeah. Yeah, and in principle that solves the problem. And I've kind of been a bit awkward because I've forgotten what I did. Does that make sense? Yeah, so I said suppose a squared plus 1 is a square for all a, then plus a is a function that always takes squares to squares. But so what? It's iterations, but this is impossible since iterations get everything. Yeah. So now I'm a little bit worried if I wasn't too careful about something. Yeah, you might want to check also that if you put A equals B, it can't be 0 mod P. Yeah, so if you put A equals B, for example, right, you get 3B squared, right? So that's I guess that's why 3 is special, maybe. But, yeah. Yeah. Yeah, okay. So if A equals B, you get 3B squared plus 1, right?
Yeah.
And since the 3 is invertible in these primes, yeah, you can just think of that as B squared plus 1. Yeah? Yeah?
Yeah.
So the solutions you find here are never going to be A equals B. Does that make sense?
Oh,
Because we don't have squares that equal to minus 1, right? So um, so we don't have to worry about that. So the things we found here are definitely the ones that solve the problem. Yeah?
Yeah.
Are we all in agreement?
Yeah.
Okay, good. No. So the key observations, I guess, was um, knowing it. So like I'm doing it for primes. It's like we don't use any of the theorems, but we kind of have that, that culture, like it reduces the primes because of like it's kind of Chinese remainder theorem kind of thing. And then we know like 1 mod 4 already doesn't work straight away because we know 1 mod 4 is the squares minus 1. And then we said the powers of 3 work. We need to kind of make it like 2 mod 4, yeah? We've got to show that the evens don't work. And then we reduce to this. And it's still something about squares. So it's kind of funny, like this is like what I was saying, like you don't actually have to know quadratic reciprocity, but like kind of knowing it guides you to what you're looking for. Like even having like squares mod p being a thing is like, I don't know, it's not obvious if you haven't seen it before. All right, any questions? So unfortunately, stats for like years beyond some like 2016 or something, not easy to get. But I don't know, in that year, I'm pretty sure if you did like, I gave you the stats for that, right? So this was like, cutoff was 18, 12, 8. 18, 12, 8. Yeah. Yeah. Figure out, yeah.
It's like the only place where getting 40% you can do
Yeah.
and then you get 60% off.
Yeah. All right, should I do question 2?
Hold on.
Question 2. Okay. Anyone want to help erase? So 3 was a pretty enjoyable question actually. It's one of those ones that you could really just think about. Like in a way that question 1 today wasn't that enjoyable. Like I felt like I couldn't think about it in a way that made progress without solving the problem. All right, question 2. So this question 2 in 2014, I really thought was easier than question 1. Okay. So if you kind of invested the time in understanding all the annoying notation in the question, you could solve it in like 10 minutes. Okay. So S is the set from 1 to 2014, yeah? Yeah. And then for every non-empty subset, T, okay, you get it's like one of its members is chosen as its representative. Okay. So I guess T goes to T, which was an element of T, yeah? Okay. And then find the number of ways assigning representatives to every non-empty subset if it has one condition, yeah? And the condition is anytime you have sort of 3 disjoint subsets, the representative of the union is the representative of one of the 3 sets that it's the union of. Find the number of ways to assign representative to all non-empty subsets of S. So if a subset D, so if D is a disjoint union of A, B, C, yeah? Actually, it's what a disjoint union is. So it's so in this context, okay, it's a union of 3 things that are intersect. Okay. Yeah, well, that's the point, right? So, well, in set theory, it's like, so I guess this would be like the internal disjoint union. So, like, if you have to take sets that don't intersect and then put them together, yeah. And so what you get is a subset of S, yeah. Okay. Well, I guess the proper disjoint union is like you just take any 2 sets, and even if they're not disjoint, you create the disjoint union. You'd force it. Does that make sense? So like if you had like 3 elements in one set, right, and 6 elements in the other, you would like the disjoint union would be a 9-element set where you identify 3 of them to have come from this set, and the other 6 to come from the other set. Yeah, they're different now because you've kind of thought of them as members of a different set. So it's kind of like this. You had like 1, 2. Yeah, like maybe this is S is equal to 1, 2, right? And like I shouldn't use the word S. E equals 1, 2, 3, yeah. 1, 2. So you have like T disjoint union S. It's kind of like 1S, 1T, 2S. You know what I mean? So it's like you kind of remember where the 1 comes from. Yeah. So there's 5 things, yeah. Yeah. 2, 3, 3, 2. Huh? Yeah, I guess not. You know it comes from the T. But yeah, just in case. Yeah, so this is not what they meant.
Oh.
They just meant if you had any time you had 3 sets that don't intersect. Yeah? Does that make sense? So if you're picking a representative from D, okay?
Yes, if you want to go for A.
Yeah, so if you're picking a representative from D, it has to be a representative from A, B, or C. That makes sense?
Yeah.
Okay.
So there are 3 reciprocal things.
So actually, yeah, so 3 ways given a partitioning, yeah?
Yeah.
But the thing is, there's so many ways to
Yeah.
partition, yeah? So that makes it less, right? Not
Yeah.
more. Where's the stuff? Here it is.
If you have a set of 6 things,
Yeah.
and then you like add this up as the two. So like say you have 1 to 8, and then you have 1, 2, 3, 4, 5, 6, 7, and then you take a representative from each one. Then there are 4 ways of putting this one.
Mm-hmm.
And no matter how you do it, you can the representative can't be all 4. Like the yeah. So
Basically, that's like solving the problem, I feel like. Yeah, so the key observation was n equals 4, actually. So you don't need 8.
okay.
You don't figure out n equals 4.
Yeah. So 1, 2, 3, 4. Like
Yeah, so what do we do for n equals 4, yeah? So look at this. You have 1, 2, 3, 4. And you want to assign a representative, right?
Yeah.
So let's say the representative is 3, yeah?
Yeah.
Actually, let's make it 1. Yeah? So that means 1 must be a representative, yeah?
Yeah.
Of any of those. Like you need 4 because then it's
Yeah.
2, 1, 1, yeah?
Yeah.
It's 3 is trivial, yeah? It's 1, 1, 1.
Just 1 and then.
So basically, anytime you have a subset with 1 in it, right?
Yeah.
You're forced to choose 1.
Yeah. So 1 must be big.
Yeah. Does that make sense?
Yeah.
Or another way of saying this is, if you work the other way, so if you have a subset with 2 things in it, right? It automatically excludes one of them from being the representative. Yeah?
Yeah.
So for example, if you have this set, you can take, without loss of generality, 1 is excluded, yeah?
Oh, okay.
Yeah, we haven't got the assignment.
So then it's 3, right?
Then 1 is excluded, yeah?
That's 3.
And then it could be 2, right? But then you can put 2 and 3 together.
Yeah.
So one of them has to be excluded, yeah?
Yeah. So it will be 3 or 4. And then you put 3 or 4.
And one of them has to be excluded.
And then you put 1 or 4.
Yeah. So oh no, you can get 1 out of it. Like it works, but like the point is you can only do 1. Yeah, there's no choices. Yeah, like if you've chosen the pairs, so like for example, you can only pick 1 thing, and say it's 1, right?
Yeah.
And that forces the assignments of all the representatives.
Yeah.
Can you see that? So like all the 1 element sets are obviously going to themselves, yeah?
Yeah.
And then the 2 element sets, they have to all go to 1, yeah? Okay, it doesn't force all of them, but it forces all the ones that have 1 in it, yeah?
Yeah.
3, 4, and then you can maybe think of the 3 4s as like the reasons why it couldn't have been the 3s and 4s. Or maybe this is already good enough because it excludes 2, 3, and 4, right?
Yeah.
So that forces it to be 1. So if 1 is the representative, it forces these 3 to have representative 1, right?
Yeah. Yeah.
If these 3 are representative 1, it forces that to have representative 1.
Yeah.
Because it's saying 2 can't be the representative, right?
Yeah.
Because otherwise the decomposition with this.
Oh yeah, so if those three are true, then you represent it.
Yeah. Okay. Yeah, so this point was the point where I realized this was solved. Okay. Like 2 minutes. Yeah, so maybe you want to like check it for n equals 5 or something. So, um, yeah, so I guess going forwards made it obvious that like the bigger set has no choices. It can only be one if you know the previous ones, right? Yeah. But going backwards kind of made it easier to count. If that makes any sense.
Yeah.
So basically, what like if you're going forwards, you know there's only one choice for this, right?
Yeah.
Okay. But if you go backwards, right, you know there's 4 choices for this, yeah.
Yeah.
But for every one choice, so like you pick one, yeah.
Yeah.
That forces all the subsets that contain one, yeah.
Yeah.
And then leaves the rest free.
Yeah.
Yeah. So then basically what you're doing is you exclude one and you keep going, yeah. Does that make sense? So once you assign that to be one, yeah, then all the subsets that contain one have now been forced. Yeah.
Yeah.
So the only things that are left are the subsets that don't contain one, right? Which is kind of like an induction. See, so let's go from the start, right? So like, if say you pick 2014, right?
Yeah.
There's 2014 ways to pick it. Yeah. Let's just say it's 2014.
Yeah.
Okay. And I'm saying no matter which number you pick, you get the same number of combinations afterwards.
Yeah.
So can you see all the subsets that contain 2014 have now been forced to rep 2014?
Yeah.
That makes
And
sense?
if they didn't, then 2014.
Yeah, so okay, I made a note here. There's a good note I made. So there's basically only one special caveat. So yeah, like if you have a subset that contains 2014, right? And it's not too big, yeah? Then it's gonna be one of the partitions of the union. One of the things in the union, yeah? So if it didn't rep 2014, then it would violate the condition. Right? You know what I'm saying? So like if you had a subset with 1 in 2014, yeah? That could be one set and the rest could be broken up into 2 sets. You get 3 sets, right?
Yeah.
And the representative of the whole thing has to come from one of them. Right? But you already said it was 2014, so it has to come from the one that has 2014 in it.
Yeah.
And so all the ones that have 2014 and have to choose 2014. Yeah?
Yeah.
So the only condition, the only thing that doesn't do it straight away, can you see it's the one with 2013 elements, right?
Yeah.
Because then you can't get 3, and you get 2 sets.
Yeah. So you have like 1 and then 3 else.
Yeah. So like you have like 1
And
union 2 to 2014. Yeah.
Yeah.
So this set,
it's not necessarily true.
it's not clear that it represents. It gets repped by 2014.
Because
Yeah.
there are 3 different units.
Yeah. But it is. It actually is repped by 2014. Because if you have like a subset, well, because so all the subsets that contain 2014, right, are represented by 2014. Yeah, because they don't have that problem. So I thought this was really obvious at the time, and I think it should be obvious. Should I still tell you? So I say it determines all the subsets that don't contain 2014 of size less than 2013 immediately, right? But if it's 2013 sized, it contains plenty of smaller sets, which will also make it have to be represented by 2014.
Oh, I see. Oh, you just split it into three groups that are not like that. Each one with a different where 2014 is in a different like set each time. And then
Mm-hmm. Yeah. So imagine if it's repped by something else, right? Then just put that something else
Just
in a
into the
set
set
with
2014.
2014.
Yeah, and then because you have three sets, you put like you have three representatives, one with 2014, then you have another set with those two with 2014. So
Yeah.
2014 must be.
Does that make sense? So like if it was repped by something else, like 2, right? Yeah. Then you could just put 2 and 2014 together, yeah?
Yeah.
And then union some other stuff. Yeah? And the problem is we know this set is repped by 2014 because we know all the smaller sets are repped by 2014.
Oh yeah.
Yeah?
Yeah.
All the sets that contain 2014 are of size 2012 or less
Yeah.
are repped by 2014.
Yeah. So that's one of them. Yeah, it's true.
Yeah?
Oh, what is your
Hmm?
So what is the special?
Okay.
Oh, because when the set's too big, you can't express it as a union of 3 things. Yeah.
Oh, yeah.
Yeah.
But that's something that you can express as small set.
Yeah.
This time you're splitting the one with 2014. It's a bit different, but yeah.
Yeah. Okay. So basically, there's 2014 ways to choose that first number, and then once you get rid of the first number, it's the
Everything
number of ways of doing the problem with 2013 numbers.
Yeah.
Yeah.
So, but then you keep going. So 2014.
So when do you stop? That's I guess what's the
Yeah.
base case? Yeah.
Base case is 2014.
Well, yeah, I know, but when does this argument stop?
Working. I guess like when this 3 is it gets weird.
It's like, 3. That's like going all the way to the end. So you can see like it's getting weird even when it gets to like 5 or 6. Yeah.
Yeah.
So I stopped at 6 because I was like, all right, 6 is getting far enough. Okay, so if you go to 6, so what is it? You need the subsets without the 6 to have enough in them. Yeah, so what do you need? You need like if you get to 6, right? You need to have it so when you remove 6 and you have like 1, 2, 3, 4, 5, right?
Yeah.
So you need like first of all you need all the subsets containing 6 to be defined, right?
Yeah.
So that means you have to do this argument with the size 5 sets that contain 6, right?
Yeah.
The size 5 sets that contain 6. But that's fine because 5 is big enough, right?
Yeah.
To have like
Yeah.
um
when it doesn't when it gets small. Like,
yeah.
current one.
So 4 is so 5 when you have 5 when you go to 5
And
then
then you remove 5.
the 4 elements
Oh,
sets
okay.
the container 5.
So we try that 1, 2, 3, 5.
like 1, 2, 3, 5, yeah?
When you split that into threes, like okay, you have to split that one into like another two.
So that just works, right?
Yeah, I think so.
Just works.
Wait, hang on, let me think. Yeah, I think so.
Yeah, because there's just enough. So like if it was rep by 3, right?
Yeah.
You could always put 3 and 5 together.
Yep.
And then still have 2 sets left over, yeah?
Yeah,
But that stops working the next one.
yeah, because you don't have.
You only have 3 things, yeah?
Yeah,
So you can go all the way down to 4.
yeah, and then this back to the slash.
4, yeah?
Yeah.
And that was like the original thing, yeah?
Yeah.
There's 4 ways to do that, right? So there's 4 ways to pick a number here, right?
Yeah.
That's good. So it's all the way up to basically 2014 factorial, but you stop at the 4, yeah?
Yeah.
Okay. And then once you go lower than the 4, sorry, let's pick 1 because I already have this written for 1, yeah?
Yeah.
It forces those to be done, right? But it doesn't force any of the other things.
Yeah.
So it doesn't force the 3-element subsets. And it doesn't force the other 2-element subsets, right?
Yeah.
So the other 2-element subsets, 2, 3, 2, 4, yeah?
3, 4.
3, 4. They can still be anything, yeah?
Yeah.
So there's 2 ways.
And then there's 2 ways to Asian.
This is 2 to 3. And the 3-element subsets, right?
Yeah. Yeah, the 3 elements of it, you can't split them anymore.
So there's 4 of them, right?
Yep.
And there's 3 choices for each, yeah?
3 of them, yeah.
So there's 3 to the 4.
As they matter which one.
Yeah.
It's just,
So it's going to be 2014, yeah?
Yeah.
Times 2013, all the way down to 4, yeah? And then times 3 to the 4,
times 2 to 3.
2 to the 3.
Yeah.
Yeah? Yeah. It took way longer to explain than actually to do. I think it's just a funny condition. Like if you're willing to read the question, like that's like if you're willing to like read the question and try some cases, if you do n equals 4, I think with a clear mind,
Yeah.
you can get it. Okay. And this is one of those situations where like you get it faster than question 1. I feel question 1 was kind of tricky. I don't know. Like you want the sums and products of the digits of the numbers.
Yeah.
But it's like a problem that's kind of, I don't know, the young kids like. All right. Oh yeah, juice.
Yeah.
Like, do not spill.
Yes. Juice is the only competition you have right now.
Don't spill. Oh, hold on, I'll get a cup.
There's been six, yeah, 33 days back, so now it's fine.
Steel prize. Yeah.
It's more,
Alright, body race. Race.
I'll be happy. Where did the thing go?
No?
We did the breaking one.
Oh, let's go.
Do you want to go through the questions and see if
I'm pretty sure you did it right. I just couldn't get anywhere. That's why. I was not. I didn't think I had anything good to add to it.
Oh. Because I tried proving this perpendicular, it doesn't work. So maybe we can use like the other one, the angles. But that's kind of.
Oh, question. 2015 was like crazy. It was just luck. I'm so lucky. Did you go through 2015?
I didn't try any of those. Unless maybe I did.
Oh yeah. You give it to Lisa. Yeah, I don't know. I feel like
Okay, look at the question.
that's the one. Yeah, like 2015.
Oh, like, cool. Geo question. Geo question what? I got Android. Oh, it's not the CD, it's probably the. Oh, wait, this guy. Oh, no, it's simple. Wait, have you got any all that? Not too bad. I think we got all of it. Apart from I'm not sure. Could have all the. I didn't try for. I didn't have to try. Oh, it was fine. And but the same. It was based on the number. Yeah, it was based on the number. It's like triple. But because it's okay. But they're same to you. The year between. When you say same to you, oh yeah. I was changing. Oh, I just put the same thing. Yeah.
Do you want to do question one together? I've already done it, but
Geo, okay.
I wanna recount my luck to you.
Geo and punctuation. That sounds fun.
This is like my type of test.
Yeah, exactly. Yeah.
Actually, in this test, I probably could get like 21 in 1 hour. That's how crazy this test is for me.
Geo, FE, and then like, this one's not too bad. all the outputs.
I never looked at 4 and 5 though. It could be that that's it.
Oh, yeah, we can- it's fine, whatever. Like, just do it expensive, yeah.
All right, so can we draw the? Can we just check that this diagram is right? Okay, so this is 2015 question 1, yeah.
Yeah.
All right, let's check if this diagram is right. Okay, so I drew a big circle, yeah.
Yes. Problem. Yeah, something.
Big circle, and then I drew another circle like this. Okay. And what was the condition? So
So it's just like the
A, B, C, D. Okay, so I'm not constructing the diagram like the question written, but it's kind of like the same thing, yeah. So I guess the point of this is you join the third side of the triangle. You got the third side of the triangle extended, right? And this, the point of this other circle is so that you have like these two intersections.
Yeah.
And it goes to meet that other side extended. Yeah. Okay, so that's C. That's Z. That's D, and that's X. Yeah. Oh, my diagrams suck.
What do you mean?
What? Okay, our diagram needs to be a little bit better. Oh.
Oh, okay, that's it's really the end. Yeah, zero expected.
Okay, so the point is, where's the red? Blue, maybe blue. So Z joins the D, right? To make V. And Y joins Z. W. Alright, guys, let's check this diagram, yeah? This is not a complete burn because you have a chance to actually do this while we're doing this diagram. Okay, so like let ABC be a triangle. D would be a point on side BC, yeah?
Yeah.
Such that a line through D intersects AB and X. Yeah.
Yeah.
And it goes to the ray AC at Y, yeah? Okay. And then the circumcircle BDX, yeah?
Yep.
Intersects the circle again at Z. Yeah? That's Z.
Yep.
Okay. And then the lines ZD and ZY. ZD and ZY. Intersect the circle again at V and W. Yeah? Okay. So I drew the circle first. to make it easier. So you want to show that AB equals BW, right? So another way of saying that is you want to say that the angle here, right, is related to the angle here,
Oh,
equal or they're possibly 180 minus. Yeah. Yeah, the directed angles are equal. Okay. Yeah, so I was drawing, it took me ages to draw this diagram. It was like R1 to R4 was just me failing to draw the diagram. And for some reason, remember we were doing the two circles similar switch thing? And I was like, maybe I should try and do that. Okay. But it's kind of funny because while I was doing this problem, like this diagram was like sitting on my desk, okay? Can I show you this diagram? It's sitting on my desk. It looks like this. Huh? Oh, I just wanted to see how similar it is to what we have. And you'll know when you see it. It's not a tangent. It's actually like an intersection. Maybe this is a situation where I should draw the non-circles first. Yeah, this is the diagram pretty much. Oh,
Oh. Yeah, I see. That's so.
it's basically the same, right?
Yeah, maybe.
All right, but can I just pass this around? Hey, look at the first diagram.
Oh, pivot.
Oh.
yes, that is. I'm trying to understand that question. Yeah, I don't like.
But I rarely do a geometry question quickly, but when that's like right next to me,
Oh, I see. Wait, these. I see how you know.
so can you see basically the pivot theorem is the Miguel theorem thing, yeah?
Oh yeah, yeah.
Yeah, see the triangle?
Yeah.
There's a triangle here, yeah? So this is the triangle. Yeah?
After the theorem and 4 minutes. All we did was
See?
Yeah.
So basically the point is if you have like a vertex of the triangle, right?
Yeah.
And the circle goes through like the rays, yeah? Then you take the other vertex, the circle goes through the same point of intersection on the ray. Yeah. Okay. And then you go to the last vertex, right? That vertex goes through the point of intersection of that circle on this ray, yeah? And of that circle on that ray. Yeah? And the point is that they're all intersect, yeah? Something like that. Like that, yeah?
This is the outside one.
Huh?
Just one outside. When they meet outside.
They meet outside?
Like the two sides meet outside.
Which, yes. So they meet on the side extended, yeah? Oh, you're doing the other exercises now. Alright, but you see that's the circle, yeah?
Yeah.
Yeah?
Yeah.
How does it apply here? Stuff. Should I tell you or?
ABC.
So what's the triangle?
Triangle is
AXY?
AXY.
Yeah?
And then C and B are the intersections of and then you go
So
X with you got X with B and D, and then you go
A XY, yeah?
and then you're done.
Yeah, so that big circle, right?
Yeah.
Intersects the sides at B and at C, yeah?
Yeah.
So the circle going from X has to intersect at B, right?
And then at Z,
And then it happens to go
Z, and then D.
at D, right?
Yeah. And then G. The one at D, C, and the one
And then the one is
DC,
Y, right?
Y is the one that goes through C and
Has
D
to go through C
and D,
and D,
and then
right?
it goes to Z.
And it has to go through Z because it has to intersect the other side. Yeah? That makes sense?
Yeah.
Alright, let's start it again.
Yeah.
Yeah. So the big circle intersects the two rays at B and C, right?
Which two words?
A, B.
Y and Y.
So the triangle we're looking at is the green one, yeah?
Yeah.
AXY, yeah? So the circle from that vertex, yeah?
Yeah.
Is going through this ray at B, yeah?
Yeah.
So then the circle from this vertex has to go through B, yeah? And then it goes through B and it goes through that side at D, yeah?
But I said it's the big one and
Yeah.
Z as
Yeah.
well, so that's it.
So then the one that starts at the vertex Y has to go through C and D. Yeah. Okay, because that's where they intersect the sides, right?
Yeah.
And the conclusion is it goes through C and D, but also goes through the point of intersection of the other circles.
Yeah.
So Z. So the conclusion is D
You are done.
Y is cyclic. Yeah. Yeah.
Oh, because it has a body.
Yeah.
Yeah, because this angle is like the external angle of that, right?
Yeah. Yeah.
So that's 180 minus that.
Yeah, so oh,
Okay.
Yeah.
Yeah. When you just said that, like, you have to prove those two are somewhat related. I thought like cyclic,
Yeah.
and I thought it would be like the other like theorem, like one was Miguel's point, or like
Yeah.
the other theorem could be triangle and then like yeah, then you do that, and then I saw that.
Yeah. So this is probably not what you want to have as question one, for you in particular.
Yeah.
Unless you actually do it in 1 minute, which is, and then use 4 hours for the other 4 questions. But I think if you do it in 1 minute, you might miss some points by not caring how to write it up and stuff.
Yeah.
Like I think to write it carefully, you need to spend some time, even if you know how.
I like fun when it's on the right, even like no matter how like I do it. So like
It's always funny when someone says a strategy that doesn't depend on anything. It's like strategy independent of situations. All right, is that all we need to talk about? So I guess there's some weird diagram dependencies, maybe. And I think so. Ultimately, like when you first see the question, you believe it's an angle chase, right? Like at
Yeah.
worst,
yeah.
and this confirms it, right? Because the proof of this is an angle chase.
Yeah. Yeah.
So the whole question overall is going to be an angle chase.
Yeah. And it's probably because you have a lot of cyclic quotes.
So there is an issue of whether like you can just quote the pivot theorem. Well, I don't have this kind of experience, so
it's very easy and quick. So
yeah,
Yeah, just it's a lot of cyclic quotes, right?
yeah. So it's probably safer to prove it than it is to quote it. I don't know.
Yeah.
Because this is not exactly the standard version. I don't know, like it's kind of,
Yeah.
you know what I mean? And if you're proving it, you're probably not proving it for the extensions of the triangle sides and stuff. Huh?
I know how you prove it. How do you prove it?
Oh, it's the same. It's still to find the angles. Except the angles. Yeah. But there's a more general one with the four lines. Remember? There's like 1, 2, 3, 4 lines. Yeah.
Oh.
So then there's actually, is there a circle missing? AXY is not actually a circle, right? So AXY is the missing circle. Isn't it?
Yeah.
All possible, so
Because it's like, I actually should. Yeah.
Okay.
I'm trying to do the angle trace. Right. It seems. You can do the angle trace. What angle and what is what? Yeah. Is that one? Or 181.
Yeah.
Right. I'm trying to actually do the cycle.
Yeah. I guess it's something you can come back to, even if it's like,
It's probably easy to prove without every like all the other stuff.
yeah. Or maybe like you can just state the lemma really precisely. Sometimes that's alright as well. Because like if you just if you're just using it kind of loosely, that's kind of annoying. But if you state exactly what you're using, you know, that might be better. Sort of like because you could just be like by pivot, or like find Miguel and then draw a circle and say you're done, right? And then pray that it gets all the marks. Yeah. Or you could like be like, okay, this is what I mean by pivot theorem, right? And then you draw this diagram, and then in the application you label like Y, Z.
But you may as well may as well just like
Yeah.
probably like
Yeah, but like it's obviously like gives you a lot of confidence with the problem.
examples.
It takes away sort of the uncertainty of the problem in 2 minutes.
Yeah.
Okay. Okay.
If you have them like like most other any problem with you, but then
Yeah.
and then in math like sometimes like you have to spend time.
Yeah, like physics, chemistry, they're all standard problems.
Yeah, it's been like curriculum. They're not curriculum. Well, they have curriculum. Yeah, they have their curriculum.
Yeah.
And they just like they have like knowledge you have to do.
Yeah, and like the last question could be like out of the blue, but like
Every question out of the blue is small.
all right, the question 2.
Yes, so you can't solve 1 or 0.
You can't even sub stuff that are equal,
Yeah, that's good. There's some stuff.
but I showed it.
Not equal. Oh.
All right.
If you want to try to huh? If you just lower the one that works yeah. Yeah. So what's this one? Like, what's this stuff? It's not that doesn't want to form. I don't know what to say. Okay. Yeah. Well, if you go for also fine. Oh, let's see. Start some kind of little oh no, it's like my snuggles.
I wonder how Edwin's doing.
Oh,
This is good.
Someone's connected, and it's unlisted this time, so it won't be him. David said he couldn't find it, which is weird.
He said
I can't get even open the chat.
I was looking at it a while ago, you and no, that's not the one.
If Edwin's still here, hit the like button. All right, shall we go to question 2? All right, you know what question 2 said?
Yeah.
It was like, oh, this was the one Angelo gave, I think.
Yeah.
So you have S going from 2 all the way up to something, 20, 15?
Yeah.
All right? Or is it infinite? Is S infinite?
No, yeah.
Or infinite? But it integers from 2 onwards, yeah? Well, we'll say it goes past 2015. Okay. The question is there a function from S to S that satisfies f of a times f of b equals f of a squared b squared, where a is not equal to b?
Oh yeah. That was one.
Oh, no, there's no one. There's no one.
Oh, it's so
so sad.
Maybe that was the problem. Like every problem has some sort of meta thing in it. Maybe this was it. Alright. Any ideas?
Some.
Yeah, so maybe I could spare you all my labor. Okay, so I started subbing in powers of 2. Okay.
Yeah.
Didn't really feel I got anything interesting. I subbed in a product of 3 things. Didn't feel like I got anything interesting. And then I started like, I think I started at some point just being like, okay, let's just try to define a function.
Yeah.
Okay.
It's fine.
Let's try to define a function. Okay, so I was like, okay, well, see the relation, if you know it on the primes, just like, if you know what it does on the primes, yeah,
Yeah.
like, that's not really enough to do. If you know what it does to the primes, you get like it's not even enough to know what it does on the squares of primes. Yeah.
Oh yeah.
But if you know what it does on all the square free integers, yeah, like, but the prime doesn't occur more than once, yeah, then that should tell you what it does for all the squares except for the squares of primes. Yeah?
Yeah.
Like immediately, yeah? Okay. And then if you so then you want to think about how you can get stuff like p times q squared or something. Yeah? So p times q squared is impossible to get out of a relation, right? Because the p is not squared. Yeah. So the only thing that comes out of this is squared. Yeah. Okay. Related to stuff like p squared times q to the 4. Yeah. Which can be gotten. Yeah. So like if you can get all the squares of primes, all the squares of square and all the free numbers, right? Then you can get all the square numbers, and you can also get like p squared times q to the 4. Yeah. And that sort of influences p times q squared, but doesn't determine it. You know what I mean? Because p times q squared has to sort of be a factor of that, right? Or related to a factor of something like that, yeah? So trying to define lots of stuff is difficult, okay? So I tried doing something like where I just look at I try to make it as constant as possible, you know, and then try to layer it up, yeah? Didn't work. Okay. Didn't work. And okay, then I was like, okay, let's just try and look at it for powers of a prime. Yeah? So if there is a function, then the function would have to restrict the powers of a prime. Yeah? Make sense? And it might be easier to consider powers of a prime instead of everything at once. Yeah? Okay. And here goes. So you have like p squared, p cubed, p to the 4, p to the 5, right? Yeah. And so let's call where f sends those things. Maybe like all these things like A, B, C, D. Yeah. Okay. And basically, as soon as you get past 5, they start like being determined. Yeah. Like immediately. You know what I mean? So like p6, yeah, is now p times p squared. You know what I mean?
Yeah.
All right.
Oh yeah. So now you got all the even ones above that.
Yeah. Exactly. be even, right?
Yeah.
So you're like P8 is
Yeah.
P cubed, yeah?
Yeah.
You can't do P squared. Uh, so 7 you have to kind of do it later, yeah. Oh, we can do 10, right? And we're happy doing 10 because we've still got A, B, C, D, E, right?
Yeah.
So 10 you could like quite a few. P squared, P cubed. I feel algebra is in its nature bashy. Because you can write everything explicitly. You know? Geometry, you don't even know where you're looking on the diagram. P4, yeah? P12. P14. P16. P18, yeah? So P12 is P squared P4. P5, yeah? P14. Okay. So once I started writing this 12 and 13 and 14, the 14 area, okay, I realized this problem is getting solved. Okay. Not only did I realize that, it made it very unlikely for there to be many solutions, right? Because can you see that like you have 5 variables? It's the same principle, yeah. You have 5 variables, and you're getting more and more equations that they have to satisfy. Yeah. So for example, so this is the first time something interesting happens, right? You have 2 ways of making P8. So if you have 2 ways of making P8, that's saying AD, right, equals BC. All right.
Oh yeah. Okay.
Yeah, like this is
Yeah.
F.
Yeah. Okay. That one. Yeah, because they like the.
Yeah. Does that make
And there's
sense?
gonna be more and more of that. Right? So
Yeah. So then, like,
eventually you're gonna
so what do you get from P12? P12, you get BD equals to AE, yeah? Is it AE or B? BD equals AE, yeah. CD equals BE. Yeah. Yeah, so what do you get for 14? You get CD. CD equals the A squared B equals BE equals CD. Is that what you get for 14? Oh yeah, because when you do 14, you get 6, right? Because you can do P12 times P, yeah? P6 times P. That is right.
Yeah,
This is P6P, right? P6. Yeah, so this is P squared times P, yeah? P squared times P5, yeah? And then P3, P4, yeah?
Which is CD.
Yeah? So that's A squared B equals that, is that, yeah?
Yeah.
So from that, you already get that E equals A squared from that.
All of that.
That can't happen that many times, right? Yeah. That's gonna break down pretty quick. Okay, so the real the time it really has too much is P18.
That's too bad. Yes.
Yeah, so I guess one of the things I got from the 18 one was ABC was equal to A squared C. From 18. Yeah, so what is A squared? A squared is P to the 4. And then
What's AC? AC.
C, what's C? P squared.
Yeah, especially is PP. It's like if you use it, that's like half of AP.
Oh, okay.
So that's where the AC.
Okay, so AC gives you P8.
And A is P.
Gives you P18.
PP8 which is expensive.
Oh, yes. PP8, yeah? So you do P times P8, yeah? Yeah?
Yeah.
So P8 is P times P3, yeah?
Yeah.
Yeah?
So what's the A?
Yeah.
So that's A squared C, yeah?
PC.
And then
What's AC?
ABC is probably P6, yeah? So P6,
Yeah.
P3.
Yeah, P6.
So P6, P3, yeah? Gives you P18. And then P6 is PAB, yeah? So it's ABC. You got ABC equals A squared C. So the conclusion from that
It's A equals
A equals B, right? Right?
and E equals B.
Yeah, so A equals B gives you a lot of stuff, yeah? Because then D has to be equal to E, right?
Yeah.
And then D has to equal C, yeah? Yeah? And then this would be another equation. E equals C. C equals D. What is this here? Maybe that's the last one. So this is A cubed equals A to the 4, yeah? From here.
Yeah.
No, I mean, that's not exactly the contradiction I got, but I think
Because
there's enough here.
BD equals D squared. BD equals D squared. So B.
Alright, are we following here? So we got A equals B, yeah? So if you cancel the A and B, you get C equals D. It can't be 0, yeah?
Yeah.
You put the A equals B here, you get D equals E.
Oh.
Yeah.
And you have A equals B.
And you have E equals A squared to the 4. So the only equation you haven't used, well, there's two equations. The two are in this one, yeah?
Yeah.
And C times D is just B squared, right?
So then
Is E squared.
B squared, yeah. And then B times
It's A to the 4.
A to 3.
Yeah. No, that's contradiction. A equals 1, yeah? A has to be equal 1, and it doesn't output 1. Yeah, so this was a difficult question too, I guess, because it just had no ideas. There was just no ideas at all. It was just bad.
Oh,
Are we good with that? Yeah. So I guess I would say this is a tricky functional equation question, even though the answer is very simple. It's just I don't know, like you just have to roll your sleeves up to get this one. There's nothing really clever, Would you agree? Yeah, and like my first 2 pages of rough working are just irrelevant. All right. Oh, this one. Erase. Erase.
which one is right there?
This is question 3.
Oh.
All right. Question 3. You know what question 3 says?
Yeah.
So you have this sequence, okay? Sequence, it's like a real sequence, even though you wouldn't think so until you start doing the problem. So the sequence is called good if A0 is a positive integer. Is it non-negative?
Oh, no. That's a good example. It is.
Oh, okay. And then it says, yeah, then the sequence either goes A plus 1 equals this, or AI on AI plus 2. Yeah? So they're the only ways the sequence can proceed. One of these 2 things. And it must eventually have 2014 in the sequence. Yeah? For some K, yeah? So that's already weird, isn't it? Why is that weird? Huh? Yeah, and also 2014 is not the year, but it's 2015, yeah? So like, are they just recycling the question? So the plots will thicken. Okay, and then what's the question? Is to find the smallest n for which there's a good sequence where a n equals 2014. Yeah. I mean, it's not even clear that good sequences exist, right? Yeah. So the question is a bit fishy. Yeah, there might not be a small as 10. Okay, like you want it to be n equals 0, right? Yeah.
Well, if you try it,
But the problem is it's positive integer n, right? Yeah.
Yeah.
Okay. So yeah, like you just want to start at 2014 and say you're done, n equals 0, yeah? But you can't. Because n has to be positive or something. Yeah. Okay.
maybe one instance,
So one seems to output odd stuff, yeah? Like the 1 and 2, yeah? Yeah, okay. So I guess the first observation I made was, okay, so it's obvious, like if you want to output 2014, you can just try and sub in 2014 and see how the previous thing gets, yeah? So what's interesting is that you know that if you can't sub it into 2, right? Yeah? Like if you put 2014 into here, yeah,
yeah.
you get negative AI,
Yeah.
yeah?
Yeah.
So notice the sequence starts positive, yeah?
Yeah.
And it's going to stay positive the whole way, yeah?
Yeah.
So it's going to stay rational even the whole way, yeah? So like 2, if you do it backwards, it'll get you something negative, yeah? Okay, so that doesn't work. But 1, if you do it backwards, gives you something like a fraction, like a half, right?
Yeah.
Yeah? So then you know like this problem is going to involve fractions, okay? And it's actually, so 2 doesn't work, so you have to do 1, right?
Yeah.
Okay, and when does 2 work? Well, 2 starts to work. You guys solve this. So you have like x, right? Equals AI on AI plus 2, yeah?
Yeah.
Yeah. And you solve for AI. Yeah. Like AI equals to, you know, 1 minus x. Like 2x on 1 minus x, yeah? You alright? Is it? So you get the 1 minus the x, yeah? And then it's 2x.
Yeah. The one that's
Okay. So basically this works. See, if x is bigger than 1, right? That's negative, yeah? If x is bigger than 1, it's going to be negative.
Yeah.
So x has to be less than 1. It has to be positive, yeah?
Yeah.
So this stays positive exactly when x is between 1 and 0.
Yes.
Yeah? Okay. Yeah. And that's perfect because when x is between 1 and 0, right? It's a fraction, and this is, and it has to be 1 then, right? Well, it can't, I mean, sorry, if x is between 1 and 0, it has to be 2, okay? Because if you do 1, right, the first step is to subtract 1 and then divide by 2, yeah?
Yeah.
So if you subtract 1, it's going to go negative, right? So actually, like, this is at worst a chase because if you want to work backwards from 2014, it always tells you which one to go every time. If it's bigger than 1, you got to go 1, yeah? If it's less than 1, you got to use 2, okay? So you don't have a choice.
Yeah.
So then you can't be wrong, yeah?
There's no reason.
Okay.
So do we keep-
Yeah, let me just like give you the summary of a chase, okay?
We're really going down to 991 on and
Yeah, exactly.
then you see.
That was
So
good.
let's go all the way back.
That's the first 10 steps.
Quickly.
Yeah, like
Well,
that.
let's keep going back until we get to something cool.
So you got 991, yeah?
And 1024, yeah.
And 1024, yeah?
And then you use that one.
And then,
That's the next one you do it. So it's like my
yeah, so you gotta do 2 times 991, and then you gotta do the difference. So it's 2 times 991, yeah? On 33. Yeah.
Why?
So
This is how mine is.
it's these two subtracted. Yeah. 1 minus x. So you cancel out the denominators, yeah?
Yeah.
So there's twice the numerator times denominator minus numerator. Yeah.
No.
So 2 times numerator and then denominator minus numerator is 33.
Numerator or a whole number? Isn't X like
I mean,
the entire thing?
you make the bottom.
Yeah, but you can cancel the denominators.
And you
So times the denominator here.
I see.
And maybe for 1, I could tell you it's AI equals x minus 1 on 2, yeah? Yeah. Actually, so if you notice that, if you put the denominators in, yeah, that becomes 2 times the denominator on the bottom, yeah?
Yeah.
And it becomes numerator minus denominator at the top.
Yeah.
So it's kind of like the reciprocal, the 1 and 2 are like reciprocals of each other. But making that observation. So, I don't know, if you want to apply this a few more times. So now it's bigger than 1, right?
Yeah.
So you can just keep subtracting 33 and so on, yeah? Yeah. So, for example, the next few steps get you 959 on 1056.
40. What? No, you just.
Yeah.
Yeah.
So what you do is you subtract 30, like you subtract 33 from the top, and then times by 2 down the bottom. So you basically need to find a power of 2 times 33 so that the top is less than the bottom. So it's like 2 to the 6, 2 to the 5. So 33 times 32 is just enough, because that's like 900 something, right?
Yeah.
Well, 1056. 33 times 32, and then so you minus 31 times 33 from that. You get that. Oh, because you're minusing you're minusing 1, then you're minusing 2, then you're minusing 4, then you're minusing 8, right?
Yeah.
So if you're minusing like the sum of powers of 2 is the same as minusing the next one minus 1, yeah? Yeah. Okay. Yeah, it's kind of weird, like, huh?
Is it just calculation? Not like an actual.
Yeah, but this might not be how they intended it, even though this is so natural. Like at this point, like I was like, yeah, maybe one of the reasons why I wasn't able to make any observations, I made some observations, but like, for example, like the numerator and denominators kind of stay bounded, right? So like this process does not produce like numerators and denominators bigger than like 2000.
Yeah.
So there's like it's like a finite number of it's either periodic or it's gonna get to something you want. Yeah.
Yeah.
But anyway, yeah, and then like my wife even joined in at some point. We just started calculating next term, and then like even had less observations. So we got to like 1236, 779. Let me just summarize it for you, okay?
How many steps?
Oh, okay. Um, okay, 1236 and 779. How about we finish it from here? We got 1511 on 504, yeah? Let's do the next couple of steps. 1511 on 504.
1007. Wait, 1007.
2007, yeah?
On
2008, yeah?
And that's just like 2014 and 2016. And that's just that one.
That's that one, yeah?
Yeah.
2014. Yeah?
Yeah. I mean, that's in design.
Yeah, so you just need to get back to an integer, right? Because that's A0. And A0 ended up being the thing you wanted to say. It's 2014.
So this.
So it starts at 2014 and ends up at 2014. And so n equals 60.
Wait a second. Oh, so you can put an entire page of these calculating.
Yeah.
It's actually working. 7 marks. Easy. Yeah. Oh, I could do
Huh?
it.
What I just said?
Yeah. Something.
Oh, so we did the sequence backwards, right? And we ended up with 2014. And that was the integer. So that's our starting value, A0. 2014.
Alright.
And then how many steps you took is just A60 is equal to 2014.
Ah.
Yeah?
Okay.
Yeah, so I was kind of too stupid to make any observations before it got to the answer. I mean, 60 calculations like this, how long could that take? I mean, it should take less than an hour, right?
And if you pass, it's fine.
A minute per
If you
calculation.
screw up somewhere and you're not.
Yeah, so I did make.
It's got from 12
So I did make an observation at some point that can you see that the two steps are just there's kind of conjugates of each other?
Yeah. Well, yeah, I mean, it's like.
So like basically like if it's less than one, right?
Yeah.
Then you do two, yeah? If it's more than one, you can do one, and one's the same as flipping it, doing two, then flipping it back. You notice that?
Well,
See, because if you flip it, it's less than one now, right?
yeah.
And what does two do? It just times the two to the numerator, and finds the difference on the bottom, yeah. And then when you flip it back, it's times the difference, the two times the denominator. That makes sense.
Yeah.
So like,
Well, let's see how it works out.
yeah, like you look at one of the calculations you did, yeah. So like say 991. 991 on 1024, yeah. Yeah. So if you go, that's by 2, yeah? You get to 2 times 991 on 33, yeah? Yeah. You do the reciprocal first, right? 991. And then you do the 2, but now then you do the 1 now, right? The 1 is 33 on top, yeah? Times 2 times 991.
Oh,
And then you flip it, yeah?
Cool.
Yeah.
How does this mean?
How do you go from 100
To that.
Yeah.
I used 1. So this is 2.
You're taking one account.
This is 1. This is reciprocals.
How you wanna- I think I'll put that one on.
1, so you subtract 1, then divide by 2, yeah?
Yeah.
Yeah.
Oh, okay, yeah.
But I made this way too late anyway, this observation.
So is there some cool thing you can do given this?
Yeah.
Oh.
Okay, but it requires an observation, okay?
Oh,
And this is an observation that's been sitting in front of us the whole time.
calculation requires no observation.
Calculation almost requires nothing. It just requires you to get 7 points. It's like, be eligible for 7 points. Yes, I am.
Careless.
But in some sense, this is a faulty question, yeah? I mean, it should,
Yeah.
well, I mean, unless, of course, it's testing your perseverance. It's like people stop at 55 and like, oh, I need to find an observation. And then they skip to question 5 and get destroyed.
Yeah.
It's like, yeah, like if you stop at 55, you get 0. I'm pretty sure, or 1.
Oh, yeah. Oh,
Don't you reckon?
like a badge. Yeah, probably. Yeah.
I don't know.
I feel like if you like make a mistake in 30, it doesn't hurt. You make a mistake and you do like the plus
Yeah.
500.
Because that's why you need an observation to stop you from making mistakes. Look at this. Okay, first of all, look at the fractions you get, right?
Yeah.
Add the numerator and the denominator.
Oh, you get integers.
Oh, okay. Observation yet to be made. We already made that observation.
Oh, you get 2015.
Wait, do you?
No, yeah, yes. Yes, you did.
Yeah. Oh, yeah,
Yeah.
yeah.
That's cool.
But that explains why it was not 2014, right? So
So
that observation. So now we're done. We've explained why the year number is correct.
Wow.
So then you just work from the when the difference is 1, because then now get to
Yeah. Well, if it adds up to 2015, then you know that has to end up at 2014, right? Because there's
Yeah.
only one thing plus
Yeah.
1 is 2015.
Okay.
Yeah. So what happens if you can prove it's 2015? If they add up to 2015?
so then this
Sort of in that.
Yeah.
Yeah.
I don't think it's too hard to prove. Do you want to try it?
Yeah, we can just do that.
Yeah.
First one.
Like the first one adds up to it, yeah?
Or you can prove that like they're essentially the same operation. It doesn't matter whether it's numerator or denominator because you're just adding them up. So,
Yeah.
and then
So you only have to do it for one of the
you
operations.
just stuff it into one operation. Should work. Because it's true.
Yeah.
You do.
Yeah, I guess if you kind of write up.
So, like,
Yeah.
X and Y.
So x on y, then x on y minus
No,
y.
X
So
and Y.
x on y
and
goes
Q, right?
Q goes to p on q minus 1 on 2, which is p on y, p minus y
P minus
on
Q.
2.
P minus Y. P minus Q.
P minus
P
q
minus
on
Q
2
into Q for 1 and then
and then
send to
Yeah.
Yeah.
So if you add,
you can do it for 2.
if you add it up, it's the same sum, right?
Yeah. Oh, yeah.
The sum is preserved.
Yeah, and this is option.
And you can show that it doesn't cancel, yeah?
Yeah.
Yeah. You can show there's no canceling.
Cancel.
Yeah, so what happens then when they add up to 2015 then, right? Then you can consider, so what is this? So P goes to, you get, P and Q goes to that. Yeah? Yeah.
This question is teaching us what at the year
Huh?
This question teaches us
So every question finds how the number relates and then you
how they
Just teaches you not to give up, basically, right? Yeah, if you have time, it's better to stand there and bash
Yeah.
than to leave and be bashed. Alright, so what is this?
What are we trying to do now?
So now I'm thinking, so you meant to take it mod 2015.
What?
Mod 2015.
Why are we using mods?
Huh?
Why are we using mods?
Oh, I guess. It's meant to be more obvious than me having to think about it, but it's meant to be like if we take but this is not my answer now. This is just me looking up other people's answers. If you take it in mod 2015, the formula looks nice.
Wow.
So what happens?
How do you want these fractions? You mean like.
Let's see. Was it P1 Q1? Yeah. Goes to P minus Q.
Yeah.
1 minus Q1. Go to 2Q. Yeah.
Yeah.
Oh, so it's minus 2q and 2q. Yeah.
Is it?
Yeah, because p plus q gives you 2000.
Yeah. So then this is minus 2Q1, right?
Yeah.
Or you can maybe think of it as minus 2P. Minus, maybe it's
Can you?
plus 2P1, yeah?
Yeah, plus 2p.
And that way it's in terms of P still.
So it always doubles.
2P1, and then that's 2Q1, yeah? So it doubles mod 2015. Yeah?
So you want to know the difference in one?
So it doubles mod 2015, and you know that it has to end up at the same place it started, right?
Yeah,
Because it adds up to 2015, yeah? So you need 2 to the n to equal 1 mod 2015.
Yeah. Okay.
Yeah?
Okay. And you solve that then.
Yeah. This is like the order of 2 in mod 2015. Actually, 2015 is not prime. So, I mean, 2n minus 1 is divisible by 2015, yeah? Which is equivalent to being divided by its prime powers.
Yeah.
So what is 2015?
It's like 5 and something else.
5,
403 is that right?
403?
It's right.
What's 403? 403 prime? Divided by 13, let's see.
Oh,
it's already not.
It's more than that.
It's divided by 13, sorry guys. Better luck next time.
It's 431.
31.
31, yeah.
31, yeah?
Okay. So it's bash. So you find the 5 and the 13 and 31. You take the GCD. No.
Yeah, so I think you have 3 problems here now, yeah?
Yeah.
3 separate problems. So,
Oh.
like, what's, like, there's, how many powers, how many multiples of 5 are powers of 2 minus 1?
How many?
Huh?
It'd be like a lot.
Well,
1, 2, 3. It's different.
Oh, so 2 to the 2 is minus 1 multiplied. Then squaring that gets you 1. And then it's like every 2 to
yeah. So,
Every
like, 2
4.
to the n minus 1, right? Is equal to 1 plus 2 plus 2 squared plus 2.
Yeah. Do we have to do that?
Yeah.
Can we just.
And
Just
every
look for it,
2
just like
every
have-
2 to
Whenever if we express n as like 4k plus something,
whenever
Uh-huh.
the 4k bit becomes 16, and that's congruent to 1, so that just gives
Oh.
us.
It's like
Because
2 to the 2
Okay.
is negative 1.
Yeah.
Then 2 to the.
Okay, so are you guys reaching the conclusion that that only happens if n equals 4k?
Yeah.
Huh?
Yeah.
Oh, 5.
Yeah.
Okay, well, that's pretty good.
Oh,
What about for 13?
that's it.
I mean, the nice thing about these is you can just do examples and figure out what the answer should be,
Yeah.
even if you can't like directly prove and see at the same time. You know.
Yeah.
So 13, like what power of 2 minus 1 gives you 13? Um,
So
2 to the 12 minus 1.
I don't know. Maybe.
Anything smaller? Or is that?
Oh, 64 is minus 1. So 2 to the 6 is minus 1 more 13. The 2 is not there.
Oh, what?
2 to the 12?
2 to the 6 is minus 1 more 13. So 2 to 12 is.
You're saying n equals 12.
I think it's 12.
So 2 to the 12 is
Yeah, so
144.
Hey,
Wait, sorry, no. 2 to the 12 is not what? 2048.
2048. So 2043.
2 to the
So
12
it's
is
4,000.
496.
4095 minus is a multiple of minus 1.
Minus 145, yeah.
195.
Multiple of 13.
Yeah, it is. Oh, yeah, it was 12.
Wait, so you're also saying n equals 12k?
Yeah.
Huh?
And 31 should be 5
Yeah, should be.
or 15.
So 31.
Or like a factor of 60.
Oh yeah, 5, right?
Yes.
Yeah,
5k. Yeah.
yeah. And that's
The LCM of these three numbers.
Four.
What was the answer before? 60.
Yeah.
Yeah.
the thing is,
Yeah, I don't know. Was it worth the brain? Looks like once you get lucky, you just think you were right. Like,
yeah.
so like, can you think of this in less time than bashing out 60k? So
Yeah,
that's,
actually, you
that's,
see the denominator. This should be similar.
Yeah.
Like you see the day after 10.
yeah, I guess this is also a way of getting points that's other than 0 and 7.
No, sevens is calculation.
Harder to make mistakes, yeah. What are you gonna do?
Yeah.
That's something.
Oh, but it's easier to conclude the wrong answer here, right? You're like, okay, well, it's 120. Good thing I didn't keep going. I would have had to take 120 hours, 120 minutes.
Wow.
Are we good with that?
This isn't too bad.
So, like, as you can see, like, APMO is not this, like, pristine clinic where people tailor make questions to exactly test all the people's weaknesses and stuff, right? It's just people submitting questions.
Yeah.
And stuff could end up anywhere, you know what I mean?
I'm just thinking of like a dark web forum where people just post
Yeah, it's like they're not these people who have like, you know, they're not like degrees in pedagogy. I don't know what it is like where they just think, how do I teach kids the best I can? How do I test them in a fair way? No. This is like, if you have a question, submit it, and we'll make 5 of them into the test. Okay. But you know, there've been some good ones, yeah.
Yeah.
Jeez. Yeah, if you want to see the rough working R1, R2, all the rough workings here. Oh, maybe you can help me finish this question. I haven't quite finished it because I didn't do the converse. I can interest you guys in this question. What time is it anyway?
Respect for someone.
So I'm not venturing past question 3 because I feel like the diminishing returns.
Yeah.
Because if we can get like 1 and 2 under our belt this year, I have a good shot. And then year 12 can be the year to shine. 5 out of 5. Like I feel like if you get 3 questions, it's a good result on its own, and it gives you a good case to make the team. Mm-hmm. Yeah, it's a problem 1 geometry. This one. Ugh. Let's get all this back at some point. Yeah. Oh. Actually, hopefully next year you guys can do the question 4 and 5 for me, and I can just watch and be like,
That makes sense.
yeah, that makes sense. Are you still playing that same game that you were playing last time? With that turn-based one?
Yeah.
It seems like it's always your turn.
Why are you playing with you?
No, he's playing single player right now.
Oh, well, that makes sense.
Oh, cool. It's a single player mode.
It's turn-based, and yet it's always his turn.
Yeah.
Question 1 and 3 geo.
Yes.
And then number theory 2. Functional equation 5.
Oh, Edwin's still here.
And then there's like graph theory question 4. But let's skip those.
All right, let's do.
Graph theory is weird.
Let's do it.
You can study it really well.
Erase.
Doesn't turn up. Yeah. So it's done.
Yeah, I mean, like the weird thing is it's a competition mixed with maths. It's like a weird thing, right? Because competitions, it's about like it's doing that one thing more than that other guy.
Yeah.
Yeah.
Yeah. Whereas maths is kind of like about perfection.
Pretty much.
Like sports makes sense to be competitions, you know, because most of the time the rules aren't even defined. You don't even know what the game is you're playing, but you got to win, right? All right, what's this problem say?
We say a triangle ABC is great if the following points for any point on the side BC.
Yeah, I thought this was a fun problem to think about. Okay, this is a fun problem to think about because I feel like you're gonna get it, and like you're kind of never alone in your mind without thoughts. Okay, so what's the question?
So point on BC called D.
Oh, okay. So you have a triangle, yeah,
Yeah, and then you got the
and it's great. ABC. It's D, right? You drop the perpendiculars, so it's like the pedal point, yeah.
Yeah, reflected.
Yeah.
And,
So if you draw a triangle, yeah.
Yeah. Oh, yes. This one.
Have you tried this one?
But, is it like? Is this
Yeah.
one? We were. No, never mind.
You have D, right? So a triangle is called great.
Yeah.
If you can put any point D on BC,
Yeah.
do the perpendicular thing,
And they're
and then reflect D, and then D lies on the circumcircle, the reflection. Yeah.
Yeah.
So that's like great if that happens. Yeah. Does that make sense?
Yeah.
Okay, and then the question actually makes it easier, I think, by actually telling you what the statement is. It says, prove that a triangle is great if and only if angle A is 90 degrees and AB equals AC.
Ah.
So basically, it's a fun problem. I mean, prove it basically this is 90 and these two are the same, yeah? Okay. And maybe you can help me because I didn't actually do the case where, because it says if and only if
Those are BP and DPR.
BP
And DPR same for those.
B
DP.
DP B.
Like the perpendicular on the AB.
Oh,
Because it's more
you mean this point here? P
Yeah.
is
equal to B.
BP.
Is it not? Wait,
If it's 9 degrees.
it is 90.
Wait, what's 9 degrees?
That's 9 degrees and it's isosceles.
Oh,
Then like the two is more.
yeah. Then they wait. If this isosceles, that'd be 45.
Yeah,
Right?
45, 45. And
45. Yeah, then they'd be equal.
Second.
Yeah.
And which means like the
Which one are we doing? If or M?
Well, I've only done the one direction where it says if it's great, then it has to be isosceles in 9 degrees. I haven't done the direction that says if it's isosceles in 9 degrees. It's great. I don't know which one you want to do first.
Well, I've drawn the one for 90 and 80 because I said,
Oh, okay. Shall we do that then?
is that this one? That's right on there.
Let me draw the diagram again. I'm gonna draw the circle first. Okay, so you have a circle, semicircle, 90 degrees, yeah? These are equal. And then we're saying for any point D, okay? This should be the easier direction, but you never know. You don't have to think about it?
yeah.
There's so much stuff here. There's also a $1,000 annual here and there's a stocks.
I got it. Yeah.
Huh?
I got it. It's
Oh.
an angle chase.
Oh, that's interesting. Let's do it. Oh. So what do we do?
Draw the yeah.
Let me. What color should I use? So do that. It's a D, yeah.
Yeah.
D.
Draw a PQ.
P. No, it doesn't matter. P is Q, yeah.
Yeah. Draw the. I guess you want to draw a reflection, like the thing was. Drawing PQ first.
And PQ.
Yeah. Draw the reflection of DP and DQ.
D. P. And then draw
Yeah,
the.
just reflect like DPQ over.
Okay,
Yeah.
like that, yeah.
Then drawing B D prime.
B.
B D prime.
Which side is B on?
B is
B.
Yeah.
D prime, yeah.
Yeah.
Oh, okay. I'm drawing in blue. Yeah.
yeah. So P D prime Q is triangle. Next one, you just want to draw D prime C.
D prime C.
Yeah. So we're proving that C D prime Q equals B D prime B D prime P. Yeah.
C.
Because this is right angle. Yeah.
Hold on a sec. So C D prime Q is equal to.
equal to B D prime P. So this is a right angle. That this plus that is also right angle, and then they're on the same arc, so then D prime will be on the circle.
Okay. So you want to show that's a right angle. You want to show
You
that's
know
a right
that
angle?
you know that's right angle.
Oh, you
because
know
reflected.
Okay.
Then if you show these two angles are the same, then that's also right.
Yeah.
Yeah. So
And then are we done then?
Yeah.
So we know that the blue makes a right angle.
yeah. So
Wait, hold on. If we know the blue makes a right angle.
then
Oh, that's on the
yeah,
side.
yeah.
Yeah. Okay.
So first, this is equal to that, and this reflector is equal to that.
Let me just draw this one. So we're trying to show that this angle here
Yeah,
right,
dot is equal to
is
that one.
equal to this angle here. Yeah.
Oh wait, no, hang on. I think I figured something out.
Is that what you're saying?
No,
Wait.
it's not.
Wait, hang on. Yeah. You proved that then, yeah.
No, it's not.
How does it start?
Oh, it starts with isosceles. D prime Q equals Q.
D prime Q equals C. Okay. Oh. So like this, yeah.
Also P D prime equals B DP.
P.
D prime equals DP.
This is P. Yeah.
Yeah.
P D prime equals DP. Yeah.
Yeah. Because reflection and DP.
Yeah.
And wait, hang on.
Oh, okay. You're saying this angle is equal to this angle.
Yeah.
Yeah.
Let me run.
So this is isosceles because they're 45.
Yeah.
And then so that's equal to that side, right? That side's equal to that side by reflection.
Yeah.
Then these two are equal. So their base angles are equal.
Yeah.
Oh, this is looking good.
Oh,
Huh?
and we just do the same thing for the other isosceles. At like Q,
Other isosceles.
so Q. Okay.
Huh?
So QC equals to QD equals to QD plus.
Yeah, it's nice.
Yeah. So the red dots that we had, the red dots.
And then use the PQD prime A as cyclic.
P Q D prime A. Oh.
Yeah.
Okay, hold on. P, Q, T. So we know the red makes a right angle, right? Yeah.
Yeah. So it's
We know there's a right angle.
into reflections.
And that means that
That means
PQ
that
A D prime is cyclic.
that means that APD prime equals AQD prime.
A P D prime. Okay, yeah.
Yeah. So then the exterior angles of the two isosceles triangles are equal. So the dots are also.
Let me just draw that in. So then you have these two angles are equal, right?
Oh yeah.
Is that what we said?
Yeah. So those are just the dots. The sum of the two dots gets exterior angles.
Oh.
So the dots have to be.
Oh. Oh, that's nice, isn't it? Yeah, that's pretty good. So what you're saying is these are two dots. Yeah. Yeah. And then here's two dots here.
Two blue, two.
Yeah.
So the dots are equal. So D prime BA equals AC D prime. So the whole thing is separate.
Uh-huh. That's pretty good. Well done, well done. Yes.
You sure you got that? Sure you got that right?
I think you both did well together.
That was nice.
Kind of missed.
Well, it's a continuation, yes. But
whole isosceles with. But otherwise,
Yeah, I saw the isosceles and I thought, oh, I'm done.
yeah, I just hated that bit too. Because it's all the cyclic bits.
yeah, that's very nice.
Cool.
So recap, I think.
Interesting. Yeah.
So what we're showing is, you know what we're showing, right?
Yeah, that's also the thing. And then you
Yeah.
have that BP and PB dash. Isosceles. Yeah. And then you have the other ones isosceles most of them are functions.
Mm-hmm.
And then you have so you have that angle and that angle, and then you have yeah, you have cyclic PD QD dash cyclic.
Yeah. Yeah, so it's a nice little problem, okay? So that's one direction, right? If it's 9, so that's the direction I didn't get, so that's good. So it was good. let me
It sounds
just.
like one where I can just do the thing back.
I need more. Yeah, I'm pretty sure you can do that. I need more people.
Yeah, well done. That was good. I like that. I approve of that.
Is this something we can like? This looks like something where we can still something back to back in zero. So this.
Oh, I failed drawing the diagram. Yeah, actually, this is a good question to think about. I don't want to burn it for you. Maybe you want to have a think about it and then we can talk about it after dinner, yeah? Actually, dinner is pretty much now. So you can still continue thinking about it after dinner. And then we can have a talk about it after you think about it after dinner.
I get which one? The common
What's
one
that?
at the back.
Assume it's great and then show it
Sure, it's
90
nice.
isosceles. What's so great about isosceles? Call a triangle right isosceles if for any point D on the hypotenuse. It's oh wait no, it's not a hypotenuse yet.
Call triangle tuning if it's not this.
Yeah, so call a triangle scalene and acute or obtuse. I wonder how Edwin's doing. Should I call him?
Maybe he did this faster than me.
Huh?
Maybe he did this faster than me. And then he speaks fine in chat. But you
Yeah. If I call him on my phone. It's probably not near his phone. Calling Edwin. Oh, hello? Whoa, he picked up the phone. Are you following? Are you following? But we're gonna break for dinner soon, but we're you know what problem we're working on, right? Do you have any questions about the other stuff? It's all good. Alright, that's good. Did you try today's test? How much did you get much in the way of question 2? Question 1.
Bash questions it. Yeah.
Oh, did you try today's paper? Alright. So I think Yeah, maybe dinner will be right now. I don't know. We probably won't go for that long, but at least half an hour. And then we'll come back. Hopefully, you've made some progress on this question. Yeah. So it's two. Is it 2016 question one?
Yeah.
Okay. All right. Let me know if you need anything. All right. Talk to you soon. All right. Bye. Oh, it's good. So he managed to find the stream. David did not.
No.
David also asked to like get the paper. I sent it on WeChat, right?
Yeah.
He's like, "Where's the paper?" And I'm like, "It's on WeChat."
Where's
And then he gets his mom to call me. Like he has like zero problem solving ability. It's basically like
wait, I got that cited document. I got the notes. So.
Hmm. Dinner time.
Still comrades.
Stand is addictive, huh?
And then later on, like Yeah, and then it was like one year, so it turned out that Jerry and him were like using each other's phones. Like one of you and Jerry used his phone, prank text me. Something stupid like that. Yeah, it was really weird. I really thought it was someone from Flying Goodbye. Prejudice. I should have known that. Not public. I still reckon it's the best thing to do. Red David's like nothing. No one's not doing nothing. It's probably not the worst. So like David's like someone who would watch that. Whereas like like see you have to do the same content. At the same time. I feel Sean used the longest time. I like what video on every time I'm talking. I think that was the right on David. Just like he's done something and he just like doesn't do it. What? You know, that's too good to do. But he's the kind of guy that's like, whatever you do, like if you just take on whatever you do, don't just like start doing the questions and write the answers on like in the line of the question. And then he gets it and does that. Just self-aware. Yeah, I told him that every time I'm on. How many times are you so fucking afraid? How many times does he say for you to just like write the solution you see that works and say that's it without any proof? How many times do you have to go through that before you realize that's not how you do the question? Oh, I solved it. It's like he doesn't even write it. It's like he doesn't even write anything. It's like it's done. Yeah, and then next time, you know how many functional grading questions that is? You know how many times you did that same thing? You know, like it comes to function. Yeah. Check the function, put it on. I'm like, there's nothing for an interaction on this. It's just like, all right, 0, 0, 0, 0, 0. That's it. Right. Identify issues. I had another student who, like, the whole parents there, oh, we want to set this. And, yeah, so we obviously need my mom, blah, blah, blah. And, yeah, he helped us with that. And I'm like, all right, well, I can help her with maths, okay? And I can make her understand maths to a point where it'll help her beyond the ATOM. It's more than just, it'll help her beyond just getting points for the ATOM, right? And he heard me wrong, and he's like, oh yes, of course, we shouldn't math just because it gives you more points for the ATOM. No, no,
Yeah.
see. This is why, like, this like client comes out, we want to pay you to do this. And I'm like, no, no. Become doctor, it is the fastest course to be a doctor. You doctor. There's lots of ways it goes wrong. It's kind of crazy. Like, but sometimes they just don't actually, they can't retain it that long. The time it takes to already long. And also, like, when they say they understand, they never really understood. They just very low critical. Like, he's saying stuff, and it's, doing stuff, and like, yes, I understand. Yeah. Pretty hard. Like, if you just this one concept, like, go to get to divide, like, go to divide by zero. Like, you could explain the guy to his face at that moment, and then yeah, and the thing is that you practice doing it, like the exercise is like Q over Q, what is that? Q is zero. Like this, or like, you know what I mean? Like, it's like, I mean, hopefully you've seen enough AP and loads that it's not like, oh, this straight Q coronavirus. Like, flu, Because I think when you see question one and you the first time or something, it's like, well, this is much harder than I'm expecting. And so I don't know how hard it can be. And then so you go like, maybe I'm spending the whole 4 hours with this question. hit like 80 in one call. And then I'm not an inside job. Like I use my like my number CM. I'll get 8 game and then I do that 80. Well, we have a good one time. Really get on the native. This is a farm on the native. This season we're not using this. Oh, you did? Yeah. Oh, nice. That thing that went on the weekend, it was like basically the US and yeah, people posting is always a problem. Once you post a problem, they have this cool feed that puts it in the list so it looks like a paper. I only made one post. I feel like we have to do something like that. There's like no Australian in the US. That's like 2017 or something. And I'm sure it's not yet. Like, yeah, I think that every chat guy was on. And a whole bunch of it's pretty funny. Like you can kind of see just how many ways there are to approach a problem by having ways people actually I couldn't really hear from that. I was hearing myself because I was talking in the lab in the screen, and I was hearing myself. I think it's very unlikely that if you could batch it, that's totally not likely. Yeah, that's weird. Like if you're better at geometry, you'll always be better at as well. Because you need that geometry to sort of stop you back. Yeah. Like it should be even easier to batch as long as it's good geometry. That's awesome. I feel like you would have I'm starting to support that for the geometry. I was like, should I send this to them? Like, there was a question of like parallelogram, the squares and sides, because it's not the squares and sides. And I was like, yeah, we'll just batch this one. But there's another one that I was kind of thinking, because I read like there's another one where it's like the squares and the sum of the sides, any quadrilateral equal to the sum of the squares, like the diagonal or something, or minus or something. No, it's like it's general. Four times this. I don't know. opposite there.
Oh, yeah, it's weird.
Yeah, so it was like the question was because if it's on y on q squared, right? If you can make the power is a two, you can make it really big, right? Q to the power of n, right? Then so basically what it looks like is like x minus q on q, right? So times it by q, then it's like qx minus p. So the point I'm trying to make is if you have like x and it makes it an integer, right? Then q times x will also make it an integer. Because the integer will make it an integer. Times q by this. Yeah. Yeah. And that's really close to the integer. Yeah. See how that works? So like some irrational thing is close to an integer. Yeah. So close enough to make their outputs the same. Does that make sense? Yeah. So if the irrational and the rational are close enough to make the outputs the same, then if they're large enough, right? Then they must be equal. Because when you get large, it's going to get big. Yeah. So then you conclude that the x is actually rational, right? It's equal to this integer minus 2q, right? So like basically the statement is that for any polynomial that satisfies that, right? If it's true, you get it with 1q at the end, where n is large compared to 3 and so on, then all the things that make the integers are actually like there's no irrational thing that makes it an integer, which is obviously false. Because you just think like x to the power of n, yeah, n through the stuff. So that actually shows that you can't get the power more than 2, or you can't get the power big, right? If you look carefully, you observe more carefully, you can't get the power more than 2. That's like a theorem. More than Ron's theorem. Yeah. So yeah. But when I was reading that, I was kind of interested, like all these number theorems from back in the day, they all got like re-scrutinized, and they were like, for applications, we need like ways to actually find these things that exist. So then like they had like these, so they had like adjectives to describe it, like effective or not effective, or like this. So now there's like a movement to make all the theorems effective. Which is kind of interesting. So like it means that you can do research on problems that used to be closed. Like, I mean, whether a problem is open or closed to you, it doesn't really make a difference. Problems still are known. It's just, I guess it's more motivating knowing that it's open and you're like, okay, to solve it. Yeah. But now all these things are open for confusion. Yeah, so you can't even increase the power to like 2.5. So that theoretically resulting was the strongest we have. hopefully today is not too tiring. Still got enough to the tank. Once we get around to it, we'll get around to it again. We'll just do the whole fun. We need to find out. Like just pretend you got into the team. Pretty much the same experience that like social. But it's weird, like I've been to so many bad conferences, I never talked to anyone. I mean that's probably my defeat the point of it. But yeah, but it's not easy. It's not like people wait to talk. Yeah, so I mean, like, I don't know, like, people, my professor was like, just go to the talks for 5 years. I kind of don't find the subject matter that interesting, because I can just read the papers. I always found that people's personalities more interesting, but then people always emphasize the facts. So it's like, I thought this guy's book, Zhang Yi Kang, this guy's book. So he's this guy who's got like, so he's like, he worked for like Starbucks or McDonald's and stuff, speaking of laws, but then like, it was a job where it was so easy to do that. He solved this pretty famous problem in industry, and then he got tenure. So I'm like, okay, so this is the guy that you can't just write off, okay? You have to like despite appearances, not prejudge him and give him a chance, right? So I'm gonna just right off the bat, okay? He's like the only one in the whole conference that uses like a tablet or someone else, whereas everyone else uses like the huge slow push. And he didn't know how to use the tablet. Okay? It was kind of crazy because this was the ICM, okay? So like this probably has the biggest audience out of any math book in the world. Okay? There's 2,000 people sitting in the audience watching this stuff. And to spend 45 minutes figuring out how to use race with the page and the tablet. Yeah, and it was pretty funny, like I was like, no, guys, he's been through this, you can't just write him off. We wait till the last 15 minutes, you know? But everyone's obviously not. And then like, yeah, and I was sitting next to this guy. I don't even think it was a field film, it's an Indian film, Andrew Bhagat. Some Bhagavan, yeah. His mom's a mathematician too. And they're both there trying to like the guy is like writing 6 words really basic, and then like trying to figure out like he needs to delete his document and stuff like that. And then these two guys were like his dad, his mom, and him. They were like from the 6 words, like, oh, he's probably trying to say this and this. Then we go his talk. The 6 words that he said. And they were doing pretty well as well. Like, oh, it's such a good idea. It's such a good idea. What idea? Yeah. So, and he gave one of the best talks ever too because he made it clear that he didn't want to prove anything. He just made it a story. And most people try to justify their statements in their talks. And as soon as they try that, they lose like 80% every time they do it. But this guy, like, he proved something like really fundamentally like important. Like it was some number and like the lowest bound that they had was like 2, and he made it like 1 or something like yeah, it's probably way on the field that I'm It's something like that. without explaining why. Like, it was two, and then like a bunch of people did some stuff, and it became like 1.8.
Yeah, wow.
Yeah, and I'm sure it kept all the people happy too, because all the people who like supposedly didn't contribute anything now have their names in it. You can do anything in that. Like this guy's PhD thesis was like some generalization of the Rubik's cube. Like the idea of the Rubik's cube. But he applied it in pure math, so it just seems that's ends in A, right? Oh, was he planning to go? Yeah, and I'm pretty sure you can enter as many people as anything as possible. I'm pretty sure US does it on like slots. I read in the rules, only 10 count. But like, the thing is, I don't know why they spend five like some people. I guess, or at least like if they don't invite someone, right? They should just make it like they can still do it if they want to, as opposed to like they have to be invited. Like I can understand if you like you don't want to invite someone that doesn't necessarily even know about it or want to do it, and then they come away from the time to get the market, which is but like making an invitation like excluding people that aren't invited is kind of annoying. Especially when it doesn't like cost anything. Or like if it does, you can just charge the person. Like, this one's the perfect one for that people do. You don't like it's kind of like one of the towns, right? You don't have to go overseas. Yeah, I'm pretty sure Singapore probably just saying it's like let's not do it. all your natural instincts like go from the start. That's right. So I do think the impression of losing the stats, like Australia has a shortage of talent, but they never seem prepared for any of this competition. Like you know what I'm saying? Like it's like the hardest 12 in the world. Thank you. Actually getting stuff like that. 0.0007. But Leon's pretty useless in the pool though. Oh, you mean like actual like the long run? Is Jerry gonna do anything? So there must be just
Wait, this actually happened. It's only just because you just thought, like, you have all this stuff here. Maybe you spend. Oh, this one. No.
Back into existence.
Oh, it appears something's imaginary is just minus itself, and it's 0.
The Bashi
And I'm thinking of the previous problem.
Oh.
I did.
Oh yeah, like if you conjugate, you get negative.
Yeah, yeah, yeah. So it should be 0. Oh wait, no, then that's yeah, it should be correct. Yeah. I forgot about that. Wait.
Oh, so your thing work?
Yeah, I'm pretty sure it should.
Maybe we can go through it later.
think I found what it was.
Hmm.
Maybe not.
Wait, so it's equal to its inverse negative conjugate, right? Like if it's purely imaginary.
Huh?
It's equal to its negative. Wait, no. Like it's equal to the negative of its conjugate.
Yeah.
Okay.
5 minutes.
feel it so many times.
Oh, show me quiz right
Huh?
now.
Got it.
No, I've given
Oh.
up. Oh, I could do it. I probably can't do it. Just 2 minutes. Back. Oh.
Yes. How you guys going with that? I saw the stats for that year, and I let you have some more time because I think
Still, especially.
Only circles.
Irving almost there. How's it going?
If Melanka is the other way, you have two conditions that you put in one, and then this way you have one condition you try to put both other
Oh yeah. You can prove them one at a time.
conditions.
Like you can show us 9 degrees first or something.
I feel like if you get one, you
get that.
Yeah. You probably have to get both.
Yeah, I'm pretty sure you do.
It all hinges
On like that.
on you
thing
need
that-
both things.
Yeah, wait, no.
Oh,
if you have it 9, you can probably like
You
if
get
two
two
of them,
things,
you can
it's
probably
like-
choose one of them. Yeah, if you have 2 of them, you can probably choose the other.
Yeah, like I think one of the first things I said was like if you can show it's isosceles, that's also 9 degrees, but that doesn't really help that much. But should I go through it?
I don't really have. I think what you have. Like nothing. What is this?
That the 2 points where the 2 perpendicular, like the 2 feet of the perpendiculars.
Yeah.
And A and D dash is a like
Yeah,
isosceles triangle.
Yeah, yeah.
Yeah,
This is
yeah, this is
Alright, so I reckon if I give you like 2 more minutes, I can still finish before 8.
Okay.
This is about the best I can.
2 more minutes. We're not gonna get
Pressure,
anywhere
pressure.
from
An absolute ton of circles passing through D dash. A ton of circles pass through D dash.
Oh,
When you use like, I don't know if there's a complete quadrilateral
yeah, I'm trying to like
or like use value axis.
But don't forget it's question 1, yes?
Don't forget how quickly you got out of it.
That's very cool.
I'm trying to prove it cycle pendulum.
Yeah, I think this it passes through the center. Maybe this is circumstance. It's the cycle flexible.
Oh, yeah.
Yeah, it is. If it works. Prove the
That's very cool. Like when I
APQD
try to do that, I
is like,
just
but if you get that A,
it's like circular.
if you get like the other ones, then
Look at it, 'cause
Yes.
if you get the other ones like the same,
But when you get passes through
Oh.
the center. How do you get that passes through the center?
we don't, but that's what I suspect as well. If you try to if you try to prove that, you end up trying to prove the exact same thing. You have to prove the thing.
Alright. Yeah, so I guess I made this observation at the beginning
No, I don't think it's possible.
that if it's isosceles, then it's 9 degrees. You guys could show that, right?
Most likely.
Like if it's isosceles. Yeah.
Yeah.
I guess you could just pick the middle. Yeah. And these are all equal. So if it's isosceles, yeah. You take D to be the middle. What do you have?
Oh shit, yeah, we should probably like pick points to do this. Like that. Yeah. We can pick specific cases.
Oh, I see. Okay.
And that specific case has to be true.
Yeah. So like one thing I've always taken with me with like when you have a like you have to use a statement for all D, right?
Yeah.
Then it's basically like choosing.
The best thing.
Yeah, you're like the best choice of D like is basically what the competition becomes. Yeah.
Yeah.
Best choice of D. So that's a problem for mathematicians. It's like when you have choices, that's when you can go wrong, right? But it's also when you can go sort of better than other people. It's kind of when the choices happen. Like when there's no choice, you have to be right. Yeah. Okay. So I don't know. I said if it was isosceles, then you could say it was 90 degrees. Is that obvious? Huh?
Yeah.
Because by symmetry,
Yeah, you get.
it's basically a kite, right?
Yeah.
And so like
But if you choose to be as well.
Oh yeah, and then it would have to like reflect over.
yeah. then they would have to both be 90 degrees.
Yeah.
Oh, it's reflected. Oh,
Yeah, because you can't have like a weird kite.
Yeah.
By symmetry, like the longer side is not going to make it to the reflection, right? They have to be.
Oh,
that's-
yeah. I had kind of that idea when I was drawing it. It's
Yeah.
too short.
But that doesn't really help you that much because you never really prove it's isosceles first. But I think it helps you with. Okay, so pick a nice point.
The middle.
That's one nice choice. What else?
Altitude.
Yeah, another one.
Point B.
Huh? So this thing, like I always talk about with the with the sine rule thing, you know?
Oh, perpendicular. No, angle bisect.
Yeah.
Right.
Because then, like, the sides are split in the middle.
What? Oh, okay.
So remember, I keep talking about this thing, like, because we learned this from the geometry book.
Oh,
Sides are
So
split
it's
in
like-
the ratio.
You have a triangle, right?
Oh, yeah,
Yeah.
yeah.
Then you get some what?
You get stuff.
That one.
Yeah. So if you remember the point of the angle bisector, right,
Yeah.
has this
Oh.
property that every
Oh,
point of
yeah.
this line
The perpendicular
is
bisect
equidistant to the
yeah.
other two lines.
Oh.
Yeah.
That's the thing. Oh, so it must lie on the
Yeah.
and then, and then so that has to be equal to that.
Wait,
and then
what?
you do- Oh, so then you do the relationship, right? And then,
Right.
so you draw the angle bisector.
Yeah.
You get this point, you get the and then you reflect this along this, and then it has to line on this line.
Well.
Wait, what?
Yeah. So, but can you see how like
Right.
these have to be equal, right?
Yes. Yeah.
Okay. So and then these have to be equal.
Yeah.
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 So the kite, yeah.
Oh.
Then the diagonal's 90 degrees.
Yeah.
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 Oh, as bad as
Oh, so you
That's
reflect
nice.
it.
So the reflection has to lie on that line, right?
Which means it has to be that point.
It has to be that point.
Yeah. Which means it's 90 degrees. And then and then once you get 90 degrees, that's pretty good stuff. And not only is it 90 degrees, it has to be 45 degrees. And like the two. Once you get 90 degrees,
Then it's 45.
then
Okay.
it's then it's 99, so it's it has to be a square.
Yeah. So you can see
And then-
that gives you immediately is 90 degrees, right?
Isn't that just for one special case
Yeah.
of D?
Yeah.
But and that special case is only true when that's true, and since that has to be true for this. But, what?
No, it's true for all D. So
True
it's
for all
so
D,
if
so
you
it has to
put
be
this
true for
D,
this
it
one.
already makes it 90 degrees.
Wait, really?
Oh wow, that's cheating.
Oh,
I know, right?
Oh, any pointy. Oh, that's you. Yeah.
That's cool. Oh,
Any pointy. Oh, cool.
But don't worry, you're not alone. Okay, because I looked at the stats for that year.
that makes sense.
How much you get if you just do?
It seems like you'd get 3, which is weird. Because I didn't see anyone get 1.
The converse was easy. Yeah,
Actually, the converse wasn't that easy.
converse was hard.
Because you had there was some choices. Like I could make some wrong choices for sure. Like instead of taking the reflection, you could take the intersection of the circles, and I don't think that works out very well. Like basically, I felt like apart from doing what you did with the reflection, all the other things don't lead very well.
Isn't that the question?
Yeah, I know that's the most direct way to do it.
Wait, what?
So there's other ways
What
to
else?
get like because it's you can like that reflection is like it's not on the circle, then you show it's on the circle, right? You can also find the point that's on the circle and show that that's the reflection, stuff like that.
That's hard.
Well, that's fine.
Yes.
Because we don't get the equal sides.
But then you know.
Okay, so do you see that makes this 9 degrees?
Yeah, and you don't.
Oh,
Essentially, yeah, because you get angles.
yeah. Okay. So I mean, so yeah, one step at a time. You put the 9 degrees in there now, right?
Oh, yeah.
You can make it a semicircle.
But isn't that like not only is it 90 degrees, then once it's 90 degrees, then you get the angle of 45.
Well,
Like, because
It's 90.
once you get
does it make the angles 45?
because you have adjacent sides are equal.
Oh, he goes. So you have 9 degrees, yeah?
Yeah.
45 degree bisector, yeah?
And then, so if that's 45, and everything's 90, so it's cyclic. So if that's 45, then the sides are 45.
Yeah, so it's like a square, yeah?
Yeah.
Uh-huh.
And then,
Oh,
okay, maybe not yet. What are the words?
yeah, close. So assume it's 9 degrees now, right?
Yeah.
Oh, then you don't need to specific case.
Well, now you can pick another case.
Let's pick a nice point.
Any other case would work if you don't 90.
Is it? Do you?
Yeah.
Ah, so just pick like this.
The one you
midpoint.
want.
Which one? Oh no, yeah, midpoint's the cycle center.
Yeah, the center of the circle, yeah?
You just
Yes.
win.
And now you, yeah.
Oh, okay.
That's a good point to pick, yeah?
Yeah.
Good point.
Oh,
Funny.
Yeah, so you still have to show it, I guess. So yeah, like if you pick O to be the center, yeah? Then you get a
they're the
You
same.
get parallel, you get
Like it's bisected. Let's go to
oh yeah, so those two sides are equal.
Oh, there's parallels.
Yeah, no, and then you get that the perpendicular path of O is equal to half the side.
wait, what's this?
But you do like similar triangle, you do similar triangles with the midpoints.
This midpoint, yeah.
Yeah. So you get
Oh, they're parallel, you're saying.
Yeah.
Oh, so that's okay. That's one
and
way to
then
do it.
you have
This
midpoint zero.
Oh, this is the
one is-
midpoint.
Yeah.
So you're saying this
Oh.
line's parallel to that line.
Yeah, and
So
then
that's midpoint to midpoint.
yeah, and then and since we already know that the two paths. Right.
No, yeah.
Yeah,
Because the
Yeah.
perpendicular
Well,
bicycle is.
So the thing you did, right? You could do it for here as well.
Yeah, because
Yeah.
when you think.
Because there's no reason to do it for one and not the other. Huh? What? Are we all good?
Yeah, I understand.
Yes.
It is understood.
And then you
And then the same idea again, basically.
wait,
I mean, this is your way of doing it. I have another way of doing it, but wow, that's pretty crazy.
when you reflect it. Oh yeah, so the height of the reflection.
Yeah.
The height of the reflection has to be the same as that.
Yeah.
Yeah, and then since that's the midpoint, that has to be the like.
Yeah. So
And
this,
since since the since always the like. Since you reflect over like that line, then it gets to
yeah. So basically, this is parallel, right?
the parallel. Yeah.
Because it's midpoint now. It's the
Yeah.
third midpoint.
Yeah. So you just flip when you flip it over.
Yeah, it's twice that length. So it's this length, right?
Yeah.
So if it's the line on the circle, then twice that length is the radius. Yeah.
So that means that has to be this.
Why?
So you did it when you do the reflection, right? When you reflect across the line,
Yeah. That's H and H.
H is similar triangles.
The congruent.
Congruent.
Why can't you just do this?
Huh?
Why can't you do it like this?
Oh no! It has to lie on the
So-
circle.
H is like half like the line.
So like the condition is that the reflection has to lie on the circle. Yeah. That means 2H has to be the radius.
Yeah.
Oh, yeah.
And then when you flip it, it has to be 2H. So then that point has. And that
And that's already 2H above.
Oh, yeah. So it's the highest point.
Yeah.
So you can't.
It's the highest.
Yes.
Yeah. So I think
So 2H is the radius, right? So it has to be
Also,
like the tip.
So the
like
reflection times that thing is the
Yeah.
same point.
Yeah.
Yeah, so I think the way I did, I chased some of these angles around. So I went
So at the same point, then it's
This-
directly
this
above, so
angle,
it's 45 degrees.
this
And it's the
angle,
highest point, so it's the highest point.
that
so
angle.
it's-
Points. Yeah.
I chased these angles until I showed it was parallel. That was the main thing.
Okay. Which one's the highlight?
So the red line and the diameter.
Oh, don't, but like we knew that already.
Huh?
We pretty much knew that already.
From like the,
Yeah, no, but that was my solution. I didn't do the midpoint thing.
Oh, yeah.
So I put these angles in. I think I had to know that some of these triangles are congruent. So I knew that was a rectangle, right? That's the same as that. That's the same as that. Yeah, this is the radius. That's right.
okay.
Yeah.
So you get the same,
So these two triangles are congruent because of the radius,
and then they're congruent at the top.
and they're congruent to all of them. Yeah. So then it's parallel,
Yeah.
and then you get the same thing. Yeah. Awesome. All right. Let me talk about the stats for this. So this is something that you should be interested in because it shows that you're not far off. Okay. Not
So this
far
is-
off.
Doable if we didn't confine ourselves to how we did it conversely. Because we kept thinking about doing it backwards, right? Yeah. Like just choose cases that we found.
Yeah, two pieces.
That's the stuff for when it says for any point.
Yeah. So it means it's for all of them, right?
Yeah.
And for this one, it makes it 90.
That's cool. But I probably wouldn't have 16 angle back. I want to try like center and
Well, the center gets you something.
yeah, like midpoint and this one else.
So I think if we since we did the angle bisector first, we got that as 90 first. But if you do the midpoint first, you
Yeah,
might get that it's isosceles first.
Oh, okay. And then
But like the point is it has to be like they're the same thing, right? The altitude, angle bisector, and midpoint median are the same.
Yeah.
So they should all give you something. Okay, so in this year, Australia came 15th. Okay. 1 gold, 1 silver, 5 bronze, no honorable mentions. Okay, check it out. So if you got that question right, you would have made the list.
okay.
So 28, 23, 14, 13, 11, 11, 10, 9, 7, 7. So this is year Linus got 9.
Oh.
Yeah, but look at his weirdness how he gets 9. It's like
Oh. God.
0, 5, 0, 4, 0.
What? Okay.
Yeah. So
And he went I was
You would do
and got like it was like the hardest
Yeah,
question.
yeah.
And then like only him and like this one other guy solved it.
And then
What yours is?
2017.
yeah, or like look at Charles Lee.
So he was year 9 when he did this.
Charles Lee 30040.
300.
Yeah, you know.
You get full-
Hayden Tang 01060.
Oh, wait, hang, that's weird though. 'Cause-
Yeah, Australia's like this. It's
Wait,
just
20,
no preparation.
was it
2016.
2016.
Australia doesn't like geometry.
2016, like, oh god, 2016, yeah, Hayden was in year 7.
So
Wow.
Oh, no, mine is in year 10. But you,
Australia didn't do too well with the geometry.
yeah.
It's 1 in 3 geo.
yeah, I guess if you're in year 7, you can't really know much about geometry
Yeah,
or anything.
wait, hang on, I think Hayden only made, like, yeah, no, Hayden, made junior, like, year 6 or something. Or was it year 16,
Oh.
or maybe, I don't know.
Okay, and then for the test you did today, yeah.
Yep.
Australia did a bit better. 14th, same.
14.
They have all the honorable mentions now. No NAs.
Hey,
Oh, this is the one where James Bain got a gold.
oh,
24, 22, 21, 21, 15, 15, 14, 14, 10.
oh. Hey, so if I got 14,
Yeah, you would have made the list.
yay.
With an honorable mention, hopefully. And maybe even a bronze. So the lowest bronze is a 14. 215. So if you get 16, you get like 4/5.
You could have done it with like 4.
Yeah. But as always, 20 and above is always really good.
2 marks.
Okay, well, I'll just put here.
The Lions got 21 that year.
Oh, okay. No, that's 2017.
Yeah,
Yeah, oh, that's IMO year.
is it?
Yeah, even IMO.
Oh yeah, okay. Yeah,
This is weird thing. It's IMO silver 21.
yeah. I mean, it's a time limit thing and how
Yeah.
how prepared you come as well, right? Because if you know that 1 and 2, you have some expectations. I think it's better than having no expectations.
Yeah.
But obviously, you don't want to have like too much expectation.
Yeah.
But like, yeah, like we were saying before, like half hour, 1 hour, 2 hour, yeah.
Yeah.
But maybe if we just really want to get 3, it's like 1 hour, 2 hours.
Yeah.
Yeah.
It's like I think I tried it.
Yeah. And like,
It's not something.
yeah. So in this year, like 17, everyone got 7 except for the last person for question 1. Whereas the other year, like look at question 1 for the other year. So the 2016, the question 1 we just did, yeah.
Well,
Um.
and then you check the careers.
So yeah, we got 7, 5, 7, 5, 7, 7, 7, 4, 3, 0, 0, 3.
Oh.
Yeah.
Oh, 3, yeah, 3 is fine. Converse is like.
Oh, should I check the Koreans?
Yeah, but you wouldn't do a Converse first. Well, it,
Oh, Koreans
Yeah,
35, 35,
but
34,
for Converse is
34,
like a
33,
yeah,
31,
doesn't matter.
29,
Like,
28,
one's
28, 28.
feeling a lot easier. Yeah.
Oh, there was a Korean that didn't get 7 for question 1.
6. Oh my god.
No, 4. They got 4.
Oh, they got 4. They did the. Oh, he did the hard one. They did the hard one first. Yeah. Wait, easy one.
Oh yeah, he might have not done the Converse.
There's no way he forgot to do the Converse. What do you mean? Koreans can make it. The Converse was still on.
So maybe if and only if didn't translate.
Oh.
It just smudged into an F.
Yeah.
Alright. That's it. Yeah, that was pretty good, yeah.
Like as a Korean, you wouldn't like even like you come last in your like group and go Korea, you wouldn't think that like that's like good because like you just see like when other people compare to them, like think of them, they're like oh
Yeah, I was sure
get like
good.
40.
But
And
in
then,
our context, it's pretty good.
Yeah, and then they're like, but then when they see us, they're like, oh, they're just bad. So they're like, we shouldn't need to compare to them. And then compared to everyone else, I'm like, I actually know I'm bad. So yeah.
Well, like, I feel like Korea's secret is they probably just let everyone do it.
Oh,
You know what I mean?
yeah.
There's probably like,
I
and
feel like
more
that-
people are interested in doing it as
I
well.
feel like they have this kind of elite teams like in their Facebook.
Like
They
it's,
get paid and living behind.
The pro games.
Yeah.
Like in junior camp, Johnny showed us like some like questions, some geometry questions from like year 7 enrichment in Korea.
Yeah.
And it was like harder than like it was like probably year 10 level or like year 10 level. So like the question like the theory isn't hard, but like the like it's actually the questions are geometrically hard. And the people that are competing are the year 12s. You know.
Yeah, I think you guys got a good chance.
Maybe.
Requires that density.
I feel like if like there's like 20 people in like senior, I think, and then if everyone does it, like I know that people in senior are like better than me, so I don't know like how 14 would translate into.
Yeah, but like you don't know how they prepare, right? Like they might be like, oh, let's wait till results come out before we look at APMO. And then results come out and they're just happy for a long time. And that's it. Like
What?
like if they have no expectations for APMO, have never actually tried a paper,
Yeah.
like you could see what the smart people end up doing. 00065.
Yeah. I don't know how that.
It's like there's no doubt that that requires intelligence.
Yeah.
But like it's overall a bad result.
Yeah.
For your intelligence level, right?
Yeah.
It's not the
You
best
could
way to
have
get.
easily got it like 7, 7, 7,
No,
2,
but
2.
like some questions you were just very comfortable.
Well, like not that extent. But
Well, like I'm very comfortable with functional equations, right?
Yeah.
But question 5 still takes freaking ages to do.
Yeah, but that's like the only thing you're comfortable with. So you just spend like your entire time doing the one you're comfortable with.
Yeah, like maybe you just want the street credit. It's like, oh, I thought 1 to 4 were trivial. I just
like, cause if question 5 is what you're good at, and then everyone knows that you're good at that topic, and you actually solve it,
yeah.
then that's like pretty good.
No, but it's better than like doing everything else and getting mediocre to 0.
I guess
They're
it
not
depends
having
what
enough
you're
time
there
for
for.
the
Yeah,
problem.
like it depends what you're there for. Like, if you enjoy you enjoy whatever problem you're working on, yeah, then that's as far as I'm concerned a good time. You know, but like, if you care about the score,
Yeah. There's a solve question 5 with double inversion and complex batch.
oh,
And then,
there was an inversion. You could have inverted the one we did today. If I remember.
oh, really? Well,
Yeah, so I don't know. Like, don't like kill yourself practicing until Tuesday. It might be good to look at some other people's solutions to stuff you've already done.
oh yeah.
That might be interesting. Though, and then like if you haven't done that before either, that's annoying because then you have to delve into the notation.
I looked at the I could have the really old papers for APMO, and it looks like the questions look are really different.
Yeah, like we only did 2013 on
Yeah,
this.
I look at the 1989 one,
Yeah,
and it's like different.
yeah. So if you're interested in those, right, we can actually provide solutions. They don't have solutions for those.
Oh, I like book has some.
Oh. So the ones it's like 2004 to 19.
Oh, I only have them up to like 2009.
Oh, okay. So those guys could have just submitted it to the website. Maybe it's not worth it.
Sure.
But I think your dad's here, Sean. And your mom downstairs. She's waiting outside.
Yeah. 14. It's just identity.
Ah.
I did it.
Yes.
I win. I've achieved.
3 variable functional equations.
There's nothing weird about it. It's just arts institutions.
Yeah.
Don't assume stuff is hard, yeah. I think we have some pretty good idea how 1, 2, and 3 are going to be. Pretty sure all of it will be. If geometry is Q4, honestly, you really have like some, like unless I see something that I don't, I think I can definitely do. 你想不想？
空间啊，
他们走了。
没说啥空间啊。
这个啊，我们这儿可以自由了，都是网的了。啊，好，
那我们就是说是好的，对吗？
对。
I want. And we can exercise and run through play.